Hello there, and welcome to the Cosmographer. Somewhere on this list is a theory in which the warning we would get is exactly 0 seconds, because the thing that would reach us travels at the same speed as the news of it. 12 theories, every one of them beginning inside published science before arriving somewhere colder. Number 11 is an argument that 100 billion years from now, astronomers will look up, do everything correctly, and conclude the universe is static and eternal, and be wrong about every part of it. Number 8 is a set of 2,501 simulations in which the innermost planet's orbit stretches until it crosses the path of Venus. And number 2 is a survey of 56,000 sun-like stars that put a very specific number on how often a star like ours does something we have never once watched it do. They are ordered by one thing only: how much warning each one would give. Get comfortable and settle in. If you are the kind of person who finds the long walk through hard questions restful rather than alarming, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the time we reach number 1, the word warning will have run all the way down to nothing. Let's begin at number 12. Number 12, heat death and the dark era. This is a list of 12 theories, and every one of them begins inside real published science before it arrives somewhere colder than the paper it came from. They are ordered by a single measurement, and it is not how frightening they sound. It is how much warning each one would give us. We begin at the far end of that scale, with theories whose timescales are so long that the word warning stops meaning anything at all, and we descend from there. By the time we reach the last entry, the warning time will be 0, and it will be 0 for a reason that follows directly from the physics. Everything in between is a slow walk down that ladder, from 10 to the 100th power years, to 100 billion, to a billion, to millions, to thousands, to a single afternoon, to nothing. So we start with the ending that has been known the longest. The idea is older than modern cosmology by a wide margin. In 1854, Hermann von Helmholtz described what he called a Wärmetod, a heat death of the universe. He was working 4 decades before anyone knew there were galaxies beyond our own, and nearly 80 years before anyone knew the universe was expanding. He simply followed thermodynamics forward and did not stop when the conclusion became unpleasant. Rudolf Clausius named entropy in 1865 and stated the second law in the form that still governs the argument. The entropy of the universe tends toward a maximum. It is worth being precise about what that means, because the popular version of it is wrong. The universe does not run out of energy. Energy is conserved, that is not negotiable, and it is not what the second law says. What the universe runs out of is difference. Every process that has ever occurred anywhere, a star fusing hydrogen, a river reaching the sea, a cell dividing, a thought forming, requires a gradient. A hot place and a cold place. A high place and a low place. A concentration here and a dilution there. Work is what happens when something flows from one side of a difference to the other. When the differences are gone, the energy is still present, evenly spread, and completely useless. The modern quantitative version of this comes from Fred Adams and Gregory Laughlin, whose 1997 review in Reviews of Modern Physics, titled A Dying Universe, is still the standard map of the future. They organized it using what they called cosmological decades, simply the exponent of the number of years elapsed. The present moment, about 14 billion years in, sits at cosmological decade 10.14. That notation is useful because otherwise the numbers stop being readable. Each decade is 10 times longer than the entire history that came before it. They divided the future into 5 eras. The first is the primordial era, which covers roughly the first 10,000 years, the hot, dense phase, nucleosynthesis, the formation of the first neutral atoms. That is behind us. The second is the stelliferous era, the era of stars, which runs from about 1 million years after the beginning out to somewhere around 10 to the 14th power years. This is where we live. It is the only era in which the universe looks anything like the thing we call the universe: galaxies, starlight, planets, chemistry, weather. And here is the number that puts a human life in perspective. We are about 14 billion years into an era that lasts on the order of 100 trillion years. In terms of the total length of the age of starlight, everything that has ever happened, the formation of the galaxies, the birth of the sun, the entire history of life on Earth, occupies roughly 1/100th of 1% of it. The universe is not old. The universe is a newborn that happens to have been alive longer than we can picture. The stars that end the stelliferous era will not be stars like the sun. The sun burns for about 10 billion years, which is unremarkable. The stars that last are the smallest ones, the red dwarfs, running down to about 8% of the sun's mass, the threshold below which hydrogen fusion cannot be sustained at all. A red dwarf is fully convective, which means it circulates its entire mass through its own core, rather than burning only the central few percent, the way the sun does. That makes it grotesquely efficient. It has more fuel available to it proportionally, and it burns that fuel far more slowly. The smallest red dwarfs will still be shining in 10 trillion years. Some estimates run to 100 trillion. Proxima Centauri, the nearest star to the Sun at 4.24 light-years, is one of them, and it will outlive the Sun by a factor of roughly 10,000. When the last of them goes out, the degenerate era begins, running from about 10 to the 15th power years to 10 to the 39th. Nothing in the degenerate era is fusing. What remains is the wreckage of everything that came before. White dwarfs, the exposed cores of stars like the Sun, cooling slowly with nothing left to burn, neutron stars, spinning down, brown dwarfs that never had the mass to ignite in the first place, and black holes. The white dwarfs cool toward the temperature of the space around them, eventually becoming what are called black dwarfs, objects that no longer emit visible light. It is worth noting that no black dwarf exists anywhere in the universe today. Not one. The universe is not old enough for even the very first white dwarf ever formed to have finished cooling. The coldest known white dwarf, the companion to the pulsar PSR J2222-0137, is still somewhere around 3000 Kelvin after roughly 11 billion years of cooling, which is hotter than the surface of a red dwarf. Then the question becomes whether matter itself is permanent, and this is where the theory splits into 2 branches, both of which end in the same place. The first branch is proton decay. Grand unified theories, the attempts to show that the strong, weak and electromagnetic forces are aspects of a single force at high energy, generally predict that the proton is unstable. It should eventually decay, most commonly into a positron and a neutral pion. No such decay has ever been observed. Super Kamiokande, a tank holding 50,000 tons of ultra-pure water, a kilometer under a mountain in Japan, surrounded by more than 11,000 photomultiplier tubes, has been watching for decades. The experiment works by simple statistics. Put enough protons in one place, watch long enough, and if the lifetime is short enough, you will see one go. Nothing has gone. The lower limit on the proton's lifetime in the primary channel now stands above 2 × 10 to the 34th power years. That is not a measurement of the proton's lifetime. It is a statement that the lifetime is longer than that, and possibly infinite. Hyper Kamiokande, its successor, will push the limit by roughly another factor of 10. If protons do decay, then ordinary matter simply evaporates on that timescale. White dwarfs and neutron stars slowly lose mass. Planets dissolve. Every atom that has ever existed comes apart, and the degenerate era ends with the quiet dissolution of everything solid. If protons do not decay, Freeman Dyson worked out what happens instead in a 1979 paper called Time Without End, also in Reviews of Modern Physics. Quantum mechanics still rearranges things, just extraordinarily slowly. Nuclear reactions that are classically forbidden can still proceed by tunneling, at rates so low they are meaningless on any ordinary timescale and inevitable on this one. Over something like 10 to the 1500th power years, everything that is not already a black hole tunnels its way toward iron, the most tightly bound nucleus, the bottom of the nuclear energy valley. The universe fills with cold iron spheres, the fossilized cores of dead stars converted atom by atom into the one element that has nowhere left to go. And over a longer timescale still, those iron spheres tunnel into black holes. Either way, the black hole era arrives, roughly 10 to the 40th power, years out to 10 to the 100th. Stephen Hawking's result from 1974 sets the clock. Black holes are not permanent. They radiate, faintly, and the radiation carries away mass. The evaporation time scales as the cube of the mass, which produces numbers that stop being comparable to anything. A black hole of one solar mass takes about 10 to the 67th power years to evaporate. The largest known black holes, objects like TON 618, at tens of billions of solar masses, take something closer to 10 to the 103rd power years. And because a black hole gets hotter as it gets smaller, the process accelerates toward the end. The final moments of a black hole are not a fade. They are a flash. There is a detail here that is easy to miss. Stellar black holes are not currently evaporating. Hawking radiation from a black hole of a few solar masses is colder than the cosmic microwave background, which means those black holes are absorbing more energy from the background radiation than they emit. They are gaining mass. They cannot begin to shrink until the universe has cooled below their own temperature, which happens somewhere around 10 to the 17th power years from now. The evaporation of the black holes is not the current state of affairs. It is a phase the universe has not entered yet. And then the dark era, past 10 to the 100th power years, which is not really an era so much as a condition. What remains is a thin fog, photons, neutrinos, electrons and positrons, spread across a volume that continues to expand. The densities become so low that an electron and a positron can bind into a positronium atom whose orbital radius is larger than the entire observable universe is today. Such an atom takes on the order of 10 to the 116th power years to spiral in and annihilate. The temperature falls toward absolute zero without ever reaching it, because the accelerating expansion itself supplies a floor, a horizon temperature of roughly 2.6 times 10 to the minus 30th power Kelvin, which is as close to nothing as physics permits. That is the standard picture, and it has been the standard picture for a long time. What makes it worth telling carefully is a piece of scientific history attached to it. Freeman Dyson wrote Time Without End as an argument for optimism. He was reacting against what he saw as an unwarranted gloom in the physics community, and his conclusion was genuinely hopeful. He argued that if the universe expands forever, life could persist forever alongside it. Not by finding more energy, but by using less. A conscious system could slow itself down, hibernating between thoughts, stretching each act of thinking across longer and longer intervals as the available energy thinned. Because the intervals could grow without limit, the total number of thoughts could be infinite, even though the total energy was finite. He worked it out with real mathematics. He believed he had shown that meaning need not end. 19 years later, in 1998, two independent teams measuring distant supernovae found that the expansion of the universe is accelerating. Accelerating expansion puts an event horizon around every observer, and an event horizon puts a floor under the temperature. A floor under the temperature is precisely the thing Dyson's argument could not survive, because his entire scheme depended on the ability to keep getting colder. He acknowledged it directly. The proof did not fail because it was careless or wishful. It failed because the universe turned out to be doing something that nobody had measured yet, and that nobody had any particular reason to look for. That is worth holding on to, because it will happen again on this list, more than once. The reason this theory sits at number 12 is that its warning time is not long. It is meaningless. There is no scenario in which anything can be done, and no scenario in which anyone is caught unprepared, because the timescale exceeds not only the future of life, but the future of matter. It is the gentlest entry here. Every act any person has ever performed, a heartbeat, a sentence, a decision, was paid for by a temperature difference, and the theory simply says that the supply of differences is finite. It does not say when it runs out for us. It says when it runs out for everything. It is worth slowing down on the part of this that is already visible, because the transition into the long dark is not a future event. It is in progress, and it has been in progress for a very long time. The Milky Way currently forms somewhere between 1 and 2 solar masses of new stars each year. That is a modest rate for a galaxy of this size, and it is not the rate this galaxy used to have. Early in its history, the Milky Way was building stars at more than 10 times that pace, and the universe as a whole peaked in star formation roughly 10 billion years ago, at a redshift of about 2. Astronomers sometimes call that period cosmic noon. Every galaxy survey that looks back far enough sees the same thing. The universe was brighter, bluer, and more violent then, and it has been quieting down ever since. The gas that stars are made from is not being replenished. Each generation of stars locks a fraction of its material permanently into white dwarfs, neutron stars, and black holes, and returns the rest enriched with heavier elements. The supply thins. There is a counter-argument in the literature worth mentioning honestly, because it points the other way. A study led by David Sobral in 2012, using deep infrared surveys of star-forming galaxies, concluded that if current trends continue, roughly 95% of the stars that will ever form have not formed yet. That sounds like an abundance, and in a sense it is. But it depends entirely on assumptions about how long the remaining gas supply lasts and how efficiently it is converted, and the conclusion sits alongside the observation that the star formation rate has fallen by a factor of roughly 30 since cosmic noon. Both things can be true. The universe has a great deal of star formation ahead of it, spread very thinly across a very long time. The Sun is a third-generation star, or close to it. The carbon in a human body was manufactured in the cores of stars that lived and died before the solar system existed. The iron in blood came from supernovae. The heavier elements, the iodine in a thyroid, the zinc in an enzyme, came from processes that require the most extreme environments the universe produces. Every one of those elements was assembled during the stelliferous era, and there is no mechanism in any later era that makes more of them. The periodic table, as a working inventory, is a product of the age of starlight. When the stars stop, the inventory is closed. The degenerate era is not entirely dark, and this is one of the stranger details in the Adams and Laughlin picture. Brown dwarfs, objects that formed with too little mass to fuse hydrogen, are extremely numerous and drift through the galaxy for an unlimited time. Very occasionally, over intervals measured in cosmological decades, two of them collide. If the combined mass exceeds the ignition threshold, the collision produces a genuine star, a small, cool, ordinary red dwarf that will then burn for trillions of years. The rate is absurdly low. But the time available is absurdly long, and so the arithmetic works out to a galaxy that continues to produce a handful of new stars long after the last of the original ones has gone out. Picture a galaxy that is essentially black, containing perhaps a few dozen faint red points at any given moment, each one the accidental product of two failed stars finding each other. That is what the Milky Way looks like for the better part of 10 to the 20th power years. And the very last light is worth describing precisely, because it is not dramatic and it does not stop. The final cooling white dwarfs do not switch off. They slide down the spectrum. Their peak emission moves from white to yellow to orange to red, then out of the visible entirely into the infrared, then into the microwave, and they continue radiating at wavelengths that would require an antenna rather than an eye. There is no last visible photon in any meaningful sense. There is only a long, slow reddening across a stretch of time that dwarfs everything that came before it. And there is no observer anywhere to record the transition, which is perhaps the point. The universe does not go dark in a moment. It fades, without anyone watching, for longer than it has so far existed by a factor that has no name. One more thing about the temperature floor, because it is a genuinely modern addition to a 19th century idea. The accelerating expansion means every observer is surrounded by a cosmic event horizon, and horizons have temperatures. The horizon around us radiates faintly, at roughly 2.6 times 10 to the minus 30th power Kelvin. That is 30 orders of magnitude below the temperature of interstellar space today. It is unimaginably cold, and it is not zero, and the difference between those two statements is the entire reason the far future is a place where nothing can happen. A system at the horizon temperature surrounded by other systems at the horizon temperature has no gradient available. There is nothing left to flow. There is, however, a stranger loss coming long before the last black hole evaporates, and it is not the universe that disappears. It is the evidence. Number 11. The End of Cosmology. In 2007, Lawrence Krauss and Robert Scherer published a paper with a title that reads more like a warning than a result. They called it The Return of a Static Universe and the End of Cosmology. It won the Gravity Research Foundation's Essay Prize that year, and it has been quietly unsettling people ever since. The argument is not that the universe ends. Everything at number 12 still happens on schedule. The argument is narrower, and for some people, worse. It is that the evidence ends. That the facts we know about where everything came from are not permanent features of reality, but temporary features of our location in time, and that they are already beginning to expire. To see why, it helps to lay out exactly how we know what we know, because each piece of it is a measurement, and each measurement depends on something being visible. Start with the size of the visible universe. The observable universe is a sphere, roughly 93 billion light-years across, containing on the order of 2 trillion galaxies. That is not a guess. It comes from deep field surveys extrapolated across the whole sky. We know the universe is expanding because Vesto Slipher began measuring the redshifts of what were then called spiral nebulae in 1912, and because Edwin Hubble using Henrietta Swan-Leavitt's period luminosity relation for Cepheid variable stars to establish distances, showed in 1929 that a galaxy's recession velocity scales with how far away it is. That relationship, velocity proportional to distance, is the signature of expansion. It is visible only if there are other galaxies to measure. We know the expansion is accelerating because of a specific measurement made in 1998. Two competing teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type 1a supernovae as standard candles to measure how much the expansion had slowed down. Everyone expected deceleration, gravity pulls, and the only question was by how much. Instead, the distant supernovae came out fainter than they should have been, which means farther away than they should have been, which means the expansion has been speeding up. The result was so unexpected that both teams spent months looking for the error before publishing. It won the Nobel Prize in 2011. It is visible only if there are distant supernovae in other galaxies to observe. We know the universe began hot and dense because Arno Penzias and Robert Wilson, working on a horn antenna in New Jersey in 1965, found a persistent microwave hiss coming from every direction that they could not eliminate. They checked the equipment. They cleaned out a pair of nesting pigeons. The signal remained, and it turned out to be the cosmic microwave background, the light released when the universe cooled enough for neutral atoms to form, about 380,000 years after the beginning. It is currently at a temperature of 2.725 Kelvin. It is visible only as long as its wavelength is short enough to detect. And we know the details of the first few minutes because the observed abundances of hydrogen, helium, and lithium match the predictions of Big Bang nucleosynthesis with remarkable precision. About 24% of the ordinary matter by mass is helium, and that number is a direct fingerprint of conditions in the first 3 minutes. It is readable only in gas that has not been heavily processed by generations of stars. Every one of those 4 pillars has an expiration date, and Krauss and Scherer worked out when. Accelerating expansion has a consequence that is easy to state and hard to feel. In an accelerating universe, the recession velocity of a sufficiently distant galaxy grows without limit. Past a certain distance, the cosmic event horizon, which currently sits at roughly 16 billion light-years in co-moving terms, a galaxy's light can never reach us, no matter how long we are willing to wait. Not because it is moving through space faster than light, which nothing does, but because the space between us is growing faster than the light can cross it. And as the acceleration continues, that horizon sweeps inward through the catalogue of galaxies like a slow tide going out. Objects do not vanish abruptly. They redshift. Their light stretches, dims, and slides out of every detectable band, and then they are simply gone from the sky as an observable fact while continuing to exist as a matter of principle. The Virgo cluster, at about 65 million light-years, is already falling behind. On a timescale of roughly 100 billion years, everything outside our own gravitationally bound neighborhood will have crossed over. That neighborhood is the local group, the Milky Way, Andromeda, the Triangulum Galaxy, and something over 80 smaller galaxies spread across roughly 10 million light-years, all bound to one another by gravity strongly enough to resist the expansion. Bound systems do not expand. The Earth is not getting farther from the Sun. The Milky Way is not getting wider. Over that same 100 billion years, the local group's members fall together and merge into a single large elliptical galaxy. So consider an observer inside that galaxy, 100 billion years from now, doing astronomy. Their sky is not empty. It is spectacular. This is a large elliptical, the product of every galaxy and the local group merging, and it contains more stars than we have ever had overhead. But between those stars there is nothing. No faint smudges, no Andromeda hanging in autumn, nothing that resolves into another island under any magnification, at any wavelength, because there is nothing left to resolve. They will do the astronomy anyway, because they are as curious as we are. They will measure the velocities of the stars around them and find no systematic recession, because everything they can measure is gravitationally bound and therefore not participating in the expansion. They will conclude, from perfectly good data carefully analyzed, that the universe is static, eternal, unchanging. One island of stars in an infinite void. They will look for the cosmic microwave background and not find it. By then its wavelength will have been stretched by a factor of many billions. It will be longer than the size of their observable universe, which is not a detection problem but an existence problem. And even before that limit, radiation at those wavelengths cannot propagate through the ionized interstellar medium at all, because it falls below the plasma frequency. The background is not faint. It is unreachable in principle. They will measure the helium abundance in their galaxy, hoping to learn about the first 3 minutes, and they will get the wrong answer. 100 billion years of stellar processing will have driven the local helium fraction well above the primordial 24%. The fingerprint of the first 3 minutes will have been overwritten by the intervening history. Astronomers today have to hunt for the most metal-poor gas clouds they can find, precisely to avoid this contamination. And in that future, there will be no uncontaminated gas anywhere. So the future astronomers' conclusion is that they live in a single eternal galaxy in an unchanging cosmos, with no beginning, no expansion, and no history. It is a defensible conclusion, drawn from good measurements, honestly interpreted. And it is wrong in every particular. That is the paper's sting, and it does not stop there. Krauss and Scherer point out that this future is not an aberration or a special case. It is a general condition, and we happen to occupy a narrow early window in which the evidence is still legible. There is a temptation to treat that as good fortune and move on. The uncomfortable version of the thought is the one they actually raise. If the universe can destroy the evidence of its own history, and if it has already been doing so for billions of years, then there is no particular reason to assume that our own cosmological picture is complete. Some things may have expired before we arrived. We would have no way of knowing which things, because the way we would find out is by observing them. There is a second number in this territory that deserves saying plainly, from Krauss's work with Glenn Starkman, on what is actually reachable in an accelerating universe. Because the horizon is sweeping inward, the overwhelming majority of the galaxies currently visible in a deep field image are already unreachable. Not difficult to reach. Unreachable, permanently, by anything at any speed below light, launched at any time from now onward. They are visible and out of contact, and the two categories have already separated. When we look at the deep field, most of what we are looking at is a record of things we have already lost and do not yet realize we have lost, because the light is still arriving. The gap between what can be seen and what can be touched is the first hint of a pattern that runs through this entire list. Light is the only messenger cosmology has. Every fact in every textbook about the large-scale universe arrived here as photons, and there is no supplementary channel, no second source, no way to check. The light and the news arrive together, and when the light stops, the knowledge stops with it. That phrase is worth remembering. It comes back at the end of this list, and when it does, it will mean something almost opposite. There is one more thing worth saying about the timescale, because 100 billion years is a number that slides off the mind, The universe is currently about 13.8 billion years old. 100 billion years is roughly 7 times that. It is a long time by the standards of everything we have ever measured, and a trivial time by the standards of number 12, where the interesting events happen at 10 to the 67th power years and beyond. On the ladder, this list is descending. The end of cosmology sits only one rung down from heat death, and yet the difference between them is the difference between a universe that has stopped and a universe that has merely stopped being knowable. The second one arrives astonishingly early. Cosmology, as a science with anything to look at, is a phenomenon of the universe's infancy. There is a version of this that is not bleak, and it is worth stating because it is also true. Everything that is going to be learned about the origin of the universe has to be learned now, in the geological sense of now, in a window measured in tens of billions of years that opened when the first observers appeared and closes when the horizon does. That is a very large window by human standards and a very small one otherwise. We are inside it. The measurements are still possible. The Cepheids are still there. The supernovae are still there. The background radiation is still 2.725 Kelvin and still measurable to 5 decimal places by any group that builds the right detector. There is also a real, current example of this exact phenomenon, which makes the whole argument less abstract. The tension in the measured expansion rate, the Hubble tension, where the value derived from the cosmic microwave background sits near 67 kilometers per second per megaparsec, and the value derived from local distance ladders sits near 73, is unresolved. Something in that picture is incomplete. And the tools available for resolving it are exactly the tools that the end of cosmology argument says have a shelf life. We are debugging our model of the universe with instruments that are, on cosmic timescales, being taken away from us. It is worth standing there for a moment, because the picture is not what most people expect when they imagine an empty universe. You are on a world orbiting a star in the merged remains of the local group, 100 billion years from now. Look up. The sky is crowded. This is a large elliptical galaxy, the product of every galaxy in this neighborhood falling together, and there are more stars overhead than any human ever saw from any mountaintop on Earth. They are mostly old and mostly red, because the gas that makes blue stars was spent long ago, and the light has a warm cast to it, like a very long evening. It is beautiful. There is nothing about it that suggests anything is missing. Now look between the stars. That is where the change is. In our sky, the gaps between stars are not truly empty. A long exposure of any patch of apparent nothing fills with galaxies, thousands of them, receding into a fog of faint smudges. In this sky, the gaps stay black. Point the largest telescope this civilization can build at the darkest patch overhead and expose for a year, and the image comes back exactly as dark as it started. Not faint. Not marginal. Black. The astronomers here have built the same instruments we did and asked the same questions. They have general relativity because that can be derived. They know their own galaxy's rotation, its mass, its age. They have a physics that permits expanding solutions and a sky that shows no expansion. And so, reasonably, they set the expanding solutions aside as mathematical curiosities with no observational support. There is something almost tender about it, and something worth being precise about too. Krauss and Scherer went through the possible ways such a civilization might still catch on, and there is one. Stars get ejected from galaxies, flung out by three-body encounters near massive black holes, or by supernovae in binary systems, at speeds high enough to escape entirely. Over 100 billion years, a population of those stars will have drifted well outside the local group into the intergalactic dark, still close enough to be seen and still carrying the galaxy's spectral fingerprints. If the future astronomers can find those wanderers, measure their distances, and measure their redshifts, they would see the relationship that Hubble saw. It would be a much harder measurement than ours, requiring the identification of individual stars at enormous distances against a completely dark background. But it would not be impossible. There is a version of that future in which someone works out the whole history of the universe from a handful of runaway stars and is not believed. There is also a live scientific caveat on the entire scenario, and it should be said clearly. Everything in this entry assumes dark energy behaves as a cosmological constant, a fixed energy density that stays fixed as space expands. That is the standard model, and Planck's 2018 results give dark energy about 68.5% of the universe's energy content, against about 31.5% matter. But the dark energy spectroscopic instrument, in results released in 2024 and refined in 2025 from a survey of millions of galaxies, has produced hints that dark energy's strength may not be constant, that it may have been slightly stronger in the past and be weakening now. The evidence is suggestive rather than settled, and it is exactly the kind of result that gets checked for years before anyone commits to it. If it holds, the shape of the far future changes. A weakening dark energy could slow the horizon's advance, or eventually stop it. A strengthening one does something considerably less pleasant, which is an entry on a different list. That uncertainty does not rescue the argument. It relocates it. The point of the end of cosmology is not that one specific timeline is guaranteed. It is that the observable universe is a shrinking set, that the shrinking is already measurable, and that the relationship between what is true and what is knowable is not fixed. And there is one last piece of arithmetic that makes the whole thing feel less like a thought experiment. The universe is about 13.8 billion years old. The window in which cosmology is possible, in which there are other galaxies to see, a background to measure, and unprocessed gas to sample, opened when the first stars formed and closes over the next 100 billion years or so. Nobody knows how many civilizations occupy that window. What is calculable is that the window is roughly one part in a very large number of the universe's total future. Anything that arrives late arrives to a sky that has already been edited. A few of the specific numbers make the timeline easier to hold. The cosmic microwave background cools in inverse proportion to the scale factor, so a 1,000-fold expansion drops it from 2.725 Kelvin to below 3 millikelvin, and the expansion has a great deal more than 1,000-fold left in it. The local group contains more than 80 known member galaxies, most of them faint dwarf satellites that were only catalogued in the last few decades, and its total mass is dominated by the Milky Way and Andromeda. The nearest large structure beyond it, the Virgo cluster, sits about 65 million light-years away and contains well over 1,000 galaxies. It is close enough that its gravity measurably tugs on our own motion, and far enough that it is not bound to us and will be carried away. When people say the sky empties out, that is the first thing to go, and it is already receding. Andromeda, by contrast, is bound to us and stays. Everything on the far side of that distinction is on a one-way trip, and the distinction was drawn by the expansion rate long before anyone was here to notice which side of it any particular galaxy fell on. The deepest facts anyone knows about where everything came from are facts with an expiry date. The library is open. It will not always be, and the closing is not an event anyone will attend. Both of those losses, the heat death and the end of the evidence, sit far past the point where anything alive on this planet could witness them, which raises the more immediate question of when, exactly, this planet stops having anything alive on it. Number 10. the moist greenhouse. Most people who know that the sun will die assume that Earth's habitability ends when the sun does. 5 billion years from now, in the red giant phase, when the star swells and swallows the inner planets. That is the version in the textbooks and the version in the documentaries. The theory that belongs on this list is the one that says Earth's biosphere ends roughly 4 billion years before that the mechanism is already running, and that it has been running since before there was anything alive here to be affected by it. The Sun is a main sequence star, converting hydrogen to helium in its core at a rate of about 600 million tons per second. Helium is heavier than hydrogen, and as it accumulates, the core's mean molecular weight rises. A heavier core contracts slightly under its own gravity. A contracted core is hotter and denser, and a hotter, denser core fuses faster. The result is a slow, relentless brightening. The rate is about 1% every 110 million years, roughly 10% per billion years. This is not a speculative claim. Stellar structure is the best understood branch of astrophysics, tested against millions of stars, and this particular prediction is about as secure as anything in the field. It also works backward, which is how we know it is right. 4.5 billion years ago, when the Earth formed, the Sun was about 70% as luminous as it is today. Carl Sagan and George Mullen pointed out the consequence in science in 1972 and named it the faint young sun paradox. Run the numbers with a modern atmosphere and a dimmer sun, and the early Earth should have been frozen solid from pole to pole. The geological record shows liquid water, sedimentary rocks, and probably life within the first few 100 million years. The resolution of that paradox is the thing that makes the future frightening, because the resolution is a mechanism, and the mechanism has a limit. Earth has a thermostat. It is called the carbonate-silicate cycle, and its modern description comes from a 1981 paper by James Walker, P.B. Hayes, and James Casting. It works like this. Carbon dioxide dissolves in rainwater to form a weak acid. That acid chemically weathers silicate rocks on the continents, releasing calcium and other ions, which are carried by rivers into the ocean. There, marine organisms and simple chemistry combine them with dissolved carbon dioxide to form carbonate, which settles to the sea floor and is eventually subducted. Volcanism returns carbon dioxide to the atmosphere from the other end of the cycle. The crucial part is that the weathering rate depends on temperature. Warm the planet and weathering accelerates, drawing down atmospheric carbon dioxide faster and weakening the greenhouse effect. Cool the planet and weathering slows, allowing volcanic carbon dioxide to accumulate and strengthen the greenhouse effect. It is a negative feedback loop with a response time measured in hundreds of thousands of years, and it has kept Earth's surface within the range where water is liquid for something close to 4 billion years, across a 30% increase in solar output. It is, by a wide margin, the most important thing about this planet. And it works by consuming carbon dioxide. As the sun brightens, the thermostat compensates the only way it can, by pushing atmospheric carbon dioxide steadily lower. Over hundreds of millions of years, the concentration declines. And there is a flaw, because carbon dioxide is not just a greenhouse gas. It is the raw material of photosynthesis. Plants using the C3 photosynthetic pathway, which is the great majority of plant species, including virtually every tree, cannot fix carbon efficiently below roughly 150 parts per million. Below that concentration, the enzyme that captures carbon dioxide starts capturing oxygen instead, in a wasteful process called photorespiration, and the plant loses more carbon than it gains. C4 plants, a later evolutionary innovation that includes maize, sugarcane, and many tropical grasses, concentrate carbon dioxide internally before fixing it, and can manage down to something like 10 parts per million. Ken Caldeira and James Casting ran this forward in Nature in 1992 in a paper titled The Lifespan of the Biosphere Revisited. Their result, C3 photosynthesis fails in roughly 500 million years. C4 photosynthesis follows a few hundred million years after that. When primary production collapses, every food web on the planet collapses with it, because every food web on the planet is ultimately built on organisms that turn sunlight and carbon dioxide into sugar. Notice what kind of ending that is. It is not a heat death of the biosphere. It is a starvation. Then the water goes, and that mechanism is separate and worse. As the surface warms past the point where the thermostat can compensate, evaporation increases and more water vapor reaches the upper atmosphere. Today, the stratosphere is extremely dry because water vapor condenses out at the cold trap near the tropopause before it can rise higher. Warm the lower atmosphere enough, and the cold trap warms too, and water begins leaking into the stratosphere in quantity. Up there, ultraviolet light photodissociates water molecules into hydrogen and oxygen. Hydrogen is the lightest element, and at those altitudes a significant fraction of it exceeds escape velocity and leaves the planet permanently. This is the moist greenhouse, and it is not a theoretical construct. It is what happened to Venus. Venus today receives about 1.9 times Earth's insolation and has a surface temperature around 737 Kelvin, hot enough to melt lead, under an atmosphere 90 times the pressure of ours. And Venus has a fingerprint. Its deuterium to hydrogen ratio is about 150 times Earth's. Deuterium is heavy hydrogen. It escapes more slowly. A planet that has boiled off an ocean and lost the hydrogen to space ends up enriched in deuterium in almost exactly the proportion Venus shows. There was water there. It left. Once the process starts on Earth, it does not stop, because the oceans are the source of the water vapor that drives it. Estimates of when it starts vary with the sophistication of the climate model. Jeremy LeConte and colleagues, using a three-dimensional global climate model in Nature in 2013, found the runaway threshold at about 110% of the present solar flux, which the Sun reaches in roughly 1 billion years. Eric Wolf and Owen Toon, also using three-dimensional models with different cloud treatments, argued for a later onset, closer to 2 billion years, because increased cloud cover reflects more sunlight and buys time. The difference between those two answers is entirely about clouds, which remain the largest uncertainty in climate modeling at every timescale. The most striking recent result did not come from a climate model at all. It came from atmospheric chemistry. In 2021, Kazumi Ozaki and Christopher Reinhard published a paper in Nature Geoscience examining the long-term stability of Earth's oxygen-rich atmosphere. They coupled models of the carbon, oxygen, and phosphorus cycles with the solar brightening curve and ran the whole system 400,000 times across the range of plausible parameters. Their finding was that Earth's oxygenated atmosphere is not a permanent feature of the planet. It has a mean remaining lifespan of about 1 billion years. And when it ends fast. In their models, once the decline begins, atmospheric oxygen falls by a factor of about 1 million over a period on the order of 10,000 years. 10,000 years is nothing geologically, thinner than most sedimentary layers a person could pick up. The planet reverts to a methane-rich, low-oxygen state resembling the Archean, before the Great Oxidation Event. Oxygen has been the dominant feature of Earth's atmosphere for roughly half of the planet's life. It will not be the dominant feature for the second half. The driver is the same one as everywhere else in this entry. Declining carbon dioxide starves photosynthesis. Photosynthesis is what makes the oxygen, and without continuous production, the oxygen is consumed by weathering and volcanic gases within a geological instant. There is a phrase worth introducing here, because it is going to come back. It is worth walking through the sequence, because the order in which things fail is not the order most people would guess. The first thing to go is not heat tolerance. It is food. Somewhere between 400 million and 1 billion years from now, depending on which model you trust, atmospheric carbon dioxide crosses the C3 threshold. Forests fail first because trees are almost universally C3 plants. So do most crops, most flowering plants, and the great majority of the terrestrial plant biomass. What survives is the C4 grasses and a scattering of specialists, and they hold on for a few 100 million years more, while the concentration continues to fall toward their own floor. Animals go with the plants, in the order dictated by their metabolic demands. Large animals require large amounts of food and cannot survive a thinning food web. They disappear early. Insects and small vertebrates persist longer. In the oceans, the picture is slightly different, but the direction is the same. Marine photosynthesis depends on dissolved carbon dioxide, which tracks the atmosphere, and the phytoplankton at the base of the marine food web are subject to the same arithmetic as the plants on land. Jack O'Malley-James and colleagues modeled the tail end of this in 2013 and found something that is either comforting or not, depending on temperament. Complex life ends first, on the timescale already described. But microbial life is extraordinarily persistent. Extremophiles in deep brine pockets, in subsurface aquifers, in cave systems insulated from surface conditions, can survive conditions that would kill everything visible. Their models had microbial life continuing for as long as 2.8 billion years, most of it in isolated refuges, none of it interacting, all of it slowly running out of the same things everything else ran out of. Earth's biosphere does not end in an event. It thins and retreats underground and persists as a scattering of disconnected pockets for longer than it existed as a connected system. Then the water. Once the moist greenhouse begins, the oceans are on a one-way trip, and the time scale is measured in the hundreds of millions of years it takes to photodissociate and eject an ocean's worth of hydrogen. What is left behind is the oxygen, which oxidizes the crust, and eventually a hot, dry surface under a heavy carbon dioxide atmosphere. Whether the endpoint looks precisely like Venus depends on details of the crustal chemistry that nobody can model over that timescale, but the general shape is not in dispute. Only after all of that does the Sun leave the main sequence. That happens in roughly 5 billion years, and it is the part everybody already knows. The core exhausts its hydrogen. Hydrogen fusion moves to a shell around an inert helium core, and the star swells enormously. Klaus-Peter Schroeder and Robert Conan Smith worked out the details carefully in 2008 and calculated that the Sun will reach roughly 256 times its present radius. Earth's orbit will expand as the Sun loses mass, which helps, but the swollen star also raises a tidal bulge on the planet, and the drag from that bulge pulls Earth inward faster than the mass loss pushes it outward. Their conclusion was that Earth is engulfed. Mars survives. Venus and Mercury do not. By then, of course, nothing on the surface has been alive for 4 billion years, which is roughly the entire history of life up to the present day. The red giant does not destroy a biosphere. It destroys an archaeological site. There is one more thing worth mentioning, because it is a real proposal in the peer-reviewed literature and not a science fiction invention. Don Korikansky, Gregory Laughlin, and Fred Adams published a paper in 2001 working out whether Earth's orbit could be deliberately expanded to keep pace with the brightening sun. The method is a gravity assist. Root a large Kuiper belt object on a trajectory that passes close to Earth, transferring a small amount of orbital energy from the object to the planet. Each pass moves Earth outward by a tiny amount. Repeat the maneuver roughly every 6,000 years for 1 billion years, and the planet stays in the habitable zone. The paper is serious, and its authors were clear about the risks. An error in the trajectory of an object that large would be unrecoverable. It is included here mostly because it illustrates the scale of the problem. The most modest technological response to solar brightening that anyone has been able to devise involves moving a planet on a schedule for 1 billion years without a mistake. The numbers underneath all of this are worth stating once, plainly. The solar constant today is about 1,361 watts per square meter at the top of the atmosphere. In 1 billion years, it is roughly 1,495. That is a difference of about 10%, which sounds survivable, and would be survivable if the planet had an infinite supply of carbon dioxide to trade away. It does not. The thermostat has been spending down a finite reserve for 4 billion years, and the reserve is what runs out first. Earth's biosphere is about 4.1 billion years old on the earliest carbon isotope evidence. Complex animal life is about 600 million years old. The remaining window for complex life is on the order of 500 million years to 1 billion. Which means, if you are inclined to count it that way, that the age of complex life on this planet is somewhere past the halfway mark, and the age of the biosphere as a whole is roughly 80% used up. Nothing on that timescale is a threat to anyone alive. The reason it belongs on a list of theories that keep people awake is different, and it is about the shape of the fact, rather than its urgency. Everything else on this list is contingent. It might happen, it might not. The probability is under debate. This one is not contingent. The sun brightens because helium accumulates. Helium accumulates because fusion works, and there is no mechanism anywhere in physics that reverses it. The countdown started before there was anything here to count it, and there is no version of the future in which it stops. A fair question at this point is whether the thermostat has ever failed before, and the answer is that it has, in both directions, and that the record of those failures is one of the reasons anyone believes the mechanism is real. Between roughly 720 and 635 million years ago, Earth went through at least 2 episodes in which ice sheets appear to have reached the tropics, the Sturtian and Marinoan glaciations, sometimes grouped under the informal name Snowball Earth. Glacial deposits from that period are found at what paleomagnetic evidence indicates were low latitudes. The proposed mechanism is a runaway in the cooling direction. Ice reflects sunlight. Reflected sunlight cools the planet. Cooling makes more ice, and the feedback runs away until the whole surface is frozen and weathering essentially stops. What ended it is the thermostat working exactly as described, only very slowly. With the continents under ice, silicate weathering shut down, so the carbon dioxide that volcanoes kept emitting had nowhere to go. It accumulated in the atmosphere for millions of years until the greenhouse effect was strong enough to melt the ice, at which point the planet swung violently in the other direction into an intense hothouse. The carbonate rocks deposited immediately above the glacial layers, the so-called cap carbonates, found on multiple continents, are the chemical signature of an enormous carbon dioxide drawdown happening very fast once the oceans reopened. That episode is useful because it shows both what the thermostat can do and what its limits are. It can recover the planet from a state most people would call permanent. It takes millions of years to do it, and the swings on either side of the recovery are severe. And crucially, it works by moving carbon dioxide around. It cannot manufacture more room to work in. The other useful comparison is the Great Oxidation Event, roughly 2.4 billion years ago, when cyanobacteria had been producing oxygen for long enough that the planet's oxygen sinks. Dissolved iron, reduced volcanic gases, were finally saturated, and free oxygen began accumulating in the atmosphere. It was the single largest change in the chemistry of Earth's surface since the oceans formed, and it very likely caused a mass extinction of the anaerobic organisms that dominated at the time. The relevance here is symmetry. Ozaki and Reinhard's result is that the Great Oxidation Event has a mirror image scheduled at the far end, and that the oxygen-rich interval between them is a phase rather than a state. One clarification is worth making explicitly, because the timescales in this entry are easy to confuse with much shorter ones. The solar brightening operates at about 1% per 110 million years. Anything happening to this planet's climate on the scale of centuries is a different subject with different physics, moving roughly 1 million times faster, and nothing in this entry has any bearing on it. The carbonate silicate thermostat is a geological regulator with a response time in the hundreds of thousands of years. It is not fast enough to be relevant to anything that happens within a civilization's lifetime, in either direction. It is only relevant to the question this entry is actually about, which is how long this planet can host anything at all. Everything that protects life on this planet is thinner than people imagine. The atmosphere as a whole, if it had uniform sea level density instead of thinning with altitude, would be about 8 kilometers deep, a layer you could drive through in an hour. The ozone layer, which absorbs the ultraviolet that would otherwise sterilize the land surface, is more extreme still. If all the ozone in Earth's atmosphere were brought to sea level pressure and temperature, it would form a shell around the planet about 3 millimeters thick. Every complex organism that has ever lived on land has lived underneath 3 millimeters of gas. At this point in the list, that layer is being removed slowly by our own star over 1 billion years through a chain of chemistry that nothing can interrupt. Remember the number. It comes back later, under very different circumstances. That ending assumes the Earth stays where it is, orbiting the star it was born beside, in a galaxy that leaves it alone. At least one of those assumptions has been in doubt since 2025. Number 9. The collision that may not happen. In September of 1912, at Lowell Observatory in Arizona, an astronomer named Vesto Slipher pointed a 24-inch refractor at the Andromeda Nebula and took a spectrum. The exposure took multiple nights. Nobody at the time knew what Andromeda was. The word galaxy, in the sense we use it now, did not yet apply to anything but the Milky Way, and the prevailing view was that the spiral nebulae were structures inside our own system, clouds of gas, perhaps solar systems in formation. Slipher developed the plate and measured the positions of the absorption lines. They were shifted toward the blue end of the spectrum, and the size of the shift implied that whatever Andromeda was, it was approaching at about 300 kilometers per second. It was the fastest velocity anyone had ever measured for any astronomical object, by a wide margin, and it was the first radial velocity ever obtained for what we would now call an external galaxy. It was also, as it turned out, the wrong sign. Over the following years, Slipher measured dozens more spiral nebulae, and almost all of them were redshifted, moving away, many of them at speeds well over 1,000 kilometers per second. That catalogue of redshifts is what Edwin Hubble later combined with Cepheid distances to establish that the universe is expanding. Slipher supplied most of the velocities for the discovery of the expanding universe, and is rarely mentioned in the same sentence as it. Andromeda, Messier 31, sits about 2.5 million light-years away. It contains roughly 1 trillion stars, which makes it more populous than the Milky Way, although the two are comparable in total mass once dark matter is included. On the sky, it spans about 3 degrees, 6 times the width of the full moon, and if human eyes were sensitive enough to see its outer regions, it would be one of the most conspicuous objects in the northern sky. Its approach velocity, relative to the Milky Way's center, is about 110 kilometers per second. But radial velocity alone does not tell you whether two objects collide. Two cars approaching an intersection at the same speed may hit or may not, and the difference is entirely in the sideways motion. For a galaxy 2.5 million light-years away, measuring the sideways motion is one of the hardest measurements in observational astronomy. The apparent drift is on the order of micro-arcseconds per year, the angle subtended by a coin at a distance of thousands of kilometers. Roland van der Marel and colleagues did it in 2012. They used the Hubble Space Telescope to image the same star fields in Andromeda across 7 years of observations, measuring the positions of thousands of individual stars against a background of distant galaxies, which are effectively fixed. The transverse velocity came out small enough to be consistent with zero, meaning a nearly head-on approach. Their conclusion traveled widely. The Milky Way and Andromeda collide in about 4 billion years. The merger completes around 6 billion years from now, producing a single large elliptical galaxy, which astronomers began informally calling Milkomeda. The Triangulum galaxy, M33, about 2.7 million light-years away, is likely to participate as well, possibly merging with Andromeda first. What happens in a galaxy collision is worth being precise about, because the popular image is wrong in an instructive way. Stars almost certainly do not collide with each other. The nearest star to the Sun is 4.24 light-years away, and the Sun is about 1.4 million kilometers across. Scale it down. If the Sun were a grain of sand a millimeter wide, the next grain would be about 30 kilometers away. Two galaxies passing through each other is two clouds of widely separated sand grains passing through each other, and the probability that any two grains touch is negligible. Whole stellar populations interpenetrate without a single physical impact. What does collide is gas. Molecular clouds are enormous, tens of light-years across, and when two galaxies interpenetrate, their gas reservoirs slam into each other at hundreds of kilometers per second. The gas shocks, compresses, and collapses, and the result is a burst of star formation, briefly turning a quiet spiral into one of the brightest kinds of object in the local universe. The antennae galaxies, about 45 million light-years away, are what this looks like in progress. The other thing that collides is the central black holes. Sagittarius, A star, at the Milky Way's center, weighs about 4 million solar masses. Andromeda's central black hole is considerably larger, at something over 100 million. In a merger, the two spiral toward each other over hundreds of millions of years, transferring energy to surrounding stars, then to gas, and finally to gravitational waves, before coalescing in an event that briefly outshines the entire visible universe in gravitational radiation while producing almost no light at all. Simulations by Thomas Cox and Abraham Loeb in 2008 followed the Sun's likely fate through the merger. Their result gave roughly a 12% chance that the Sun ends up flung into a tidal tail, one of the long streamers of stars thrown out during a merger, and about a 2.7% chance of ending up bound to Andromeda's remnant instead of the Milky Way's. In most outcomes, the Sun ends up considerably farther from the galactic center than it is now, in the outer halo of the merged system, under a sky with far fewer stars in it. And then, in June of 2025, the prediction moved. till Sawala and colleagues published a reanalysis in Nature Astronomy. They used updated astrometry from the Gaia mission, whose third data release in 2022 provided positions and motions for about 1.5 billion stars, together with the Hubble measurements and improved mass estimates for the local group's members. The important addition was not a better measurement of Andromeda. It was a better accounting of everything else. In particular, the Large Magellanic Cloud. The Milky Way's largest satellite galaxy had long been treated as a minor perturbation. Recent mass estimates put it at over 100 billion solar masses, roughly 10% of the Milky Way's mass, far more than earlier work assumed. An object that large, in the position it currently occupies, exerts a real pull on the Milky Way, nudging our galaxy's trajectory off the collision course by a small but consequential amount. Sawala's team ran tens of thousands of simulations, sampling across the full range of observational uncertainties in the positions, velocities, and masses of the local group's major members. The result was not a new date. It was a probability. Roughly 50% chance of a Milky Way and Andromeda merger within the next 10 billion years. A coin flip. It is worth being careful about what that 50% means, because it is easy to misread as a discovery that the collision has been cancelled. It has not been. The merger is still entirely possible. It is simply no longer the only outcome the data supports. In the other half of the simulations, the two galaxies pass close enough to disturb each other. Tidal tails, warped disks, bursts of star formation on the outskirts, and then separate, orbiting each other on a long, slow ellipse for tens of billions of years before possibly merging much later, or not at all within the timescale examined. The uncertainty is not evenly distributed either. Most of it comes from two quantities: Andromeda's transverse velocity, which remains poorly constrained despite the Hubble campaign, and the mass of the Large Magellanic Cloud, which has been revised upward repeatedly over the last 15 years and may be revised again. Reduce the error bars on either, and the probability moves. Gaia's later data releases, and eventually direct astrometry from next-generation instruments, will tighten it further. Some history is worth inserting here, because the question of what Andromeda even is was settled surprisingly recently. In April of 1920, at the Smithsonian in Washington, Harlow Shapley and Heber Curtis held what became known as the Great Debate. The subject was the scale of the universe. Shapley argued that the Milky Way was the entire universe and that the spiral nebulae were nearby objects within it. Curtis argued that they were island universes, separate galaxies at enormous distances. Both men had good evidence and both were partly right about other things, and the debate settled nothing. It was settled 5 years later. Edwin Hubble, using the 100-inch telescope at Mount Wilson, identified a Cepheid variable star in Andromeda. Cepheids pulse with a period that depends on their intrinsic brightness, the relationship Henrietta Swan Leavitt established from her study of variables in the Magellanic Clouds. Measure the period, get the true brightness, compare with the apparent brightness, and you have the distance. Hubble's answer put Andromeda far outside the Milky Way. The universe got very much larger in a single measurement. Then, in 1944, during wartime blackouts over Los Angeles that gave Mount Wilson unusually dark skies, Walter Baade resolved individual stars in Andromeda's core and discovered that there are two distinct populations of stars with different Cepheid relationships. Correcting for that roughly doubled the distance to Andromeda and, with it, the size and age of the entire universe. The galaxy that is now approaching us is also the object that has repeatedly forced astronomy to revise the scale of everything. The local group's mass was first estimated by a related trick. In 1959, Franz Kahn and Lodewijk Voltje published what is called the timing argument. It works like this. Andromeda and the Milky Way started out moving apart with the general expansion. Gravity has since reversed that motion, and Andromeda is now approaching. Given the current separation, the current approach velocity, and the age of the universe, you can solve for how much mass must be present to have turned the motion around in the time available. Their answer required far more mass than the visible stars could account for, one of the earliest quantitative indications that most of the matter in the local group is dark. That paper predates most of the dark matter literature by more than a decade. As for what the sky looks like on the way in, the sequence has been modeled in detail. For the first 2 billion years, very little changes to the naked eye. Andromeda grows slowly larger, from 3 degrees across to perhaps 5 or 6, becoming an obviously extended object rather than a faint smudge. Around 3.5 to 4 billion years from now, in the merger scenarios, it fills a large fraction of the sky, its disk visibly tilted and its dust lanes resolved. The first close passage disturbs both galaxies, throwing out tidal tails and igniting star formation. The night sky from a world in either galaxy would show unfamiliar structures and, for a while, an unusual number of very bright young stars. The two galaxies separate, slow, and fall back together. A second passage follows perhaps 1 billion years later, and after 2 or 3 such passes, the disks lose coherence entirely, and the stars settle into the smooth, featureless ellipsoid that is the endpoint of every major merger. M33 is the wild card in the sequence. It is bound to Andromeda, roughly 1/10 its mass, and in most simulations it participates in the merger, sometimes falling in first and sometimes being flung out on a long orbit. In a small fraction of outcomes, it strikes the Milky Way before Andromeda does. All of this depends on the transverse velocity, which is the measurement that carries almost all the uncertainty. To appreciate the difficulty, the entire 7-year Hubble campaign was designed to detect a motion equivalent to watching a coin at a distance comparable to the width of a continent and seeing it shift by its own diameter. The measurement was made against background quasars as fixed reference points, and the systematic errors involved in that reference frame are of the same order as the signal. The Gaia mission does something related, but different. Gaia does not measure Andromeda's stars individually with the required precision. They are far too faint and too distant for that. What it does is measure the Milky Way's own structure and the motions of its satellites with extraordinary accuracy, which pins down our galaxy's mass distribution and its response to the Large Magellanic Cloud. It is that indirect contribution, a better model of our own galaxy's motion, rather than a better measurement of Andromeda's, that shifted the merger probability. That is a genuinely odd situation to sit with. The prediction changed not because anyone learned something new about the object that is approaching, but because someone learned something new about the object doing the approaching. There is one more comparison worth having in mind. The local group is one of the least crowded environments a galaxy can occupy. The Virgo cluster contains well over 1,000 galaxies in a volume not much larger than the local groups, and galaxies in dense clusters are strongly affected by their neighbors, stripped of gas, quenched of star formation, harassed into odd shapes. The Milky Way sits in a quiet suburb. Whether that quiet has anything to do with why there is anyone here to notice it is a question that returns, with actual numbers attached, at the very end of this list. For 13 years, the 4 billion-year collision was one of the very few genuinely long-range facts astronomy could hand to a non-specialist. It had a number attached. It appeared in textbooks and museum exhibits, and in the closing sequence of a Terrence Malick film. It was the kind of fact people repeated at dinner tables because it was concrete in a way that most cosmology is not, a specific event involving specific objects with a date. And then a better measurement of a small nearby galaxy, a galaxy visible to the naked eye from the southern hemisphere, one of the closest objects in the sky, turned that date into a coin flip. The lesson is not that the earlier science was careless. Van der Marel's team did an extremely difficult measurement well, and their result was correctly caveated in the paper, even where it was not caveated in the coverage. The lesson is that the confidence was a function of what had been measured, and something large and close by had not been measured well enough to be included properly. That pattern, a prediction that looks solid until a nearby, apparently minor object is measured properly, recurs at several points on this list. It is worth carrying forward. There is a second reason this entry belongs here, and it has to do with how the collision interacts with everything else already discussed. If the merger happens, it accelerates the arrival of number 11. A major merger uses up a galaxy's cold gas in a burst of star formation and leaves behind a gas-poor elliptical that forms few new stars. The merged system would be the dominant structure of the local group, and by the time the cosmic event horizon has swept the rest of the universe out of view, it will be the only structure. The one galaxy the future astronomer sees overhead is the object this collision produces. And if the merger does not happen, if the galaxies pass and separate, the outcome is arguably stranger. Two large galaxies, bound to each other, orbiting slowly in an otherwise empty sky for 100 billion years. The future astronomer in that version has exactly one other galaxy to look at and no third object to use for comparison. Neither version has any bearing on anything alive. By the time either happens, the Sun will have left the main sequence, expanded, shed its outer layers, and settled into a slowly cooling white dwarf. Earth's biosphere will have ended, on the timescale described at number 10, roughly 3 billion years before the galaxies arrive. If there is anything watching the collision from this solar system, it is not anything descended from anything here now. What makes this entry unsettling is not the physics. The physics is gentle. A galaxy merger is one of the slowest and least violent large-scale events in nature, and any individual star passes through it without incident. What is unsettling is the epistemics. This was the most secure long-range prediction in the field. It had survived a decade of scrutiny. It was as close to a fact about the far future as anyone was going to get. And it moved. Every remaining entry on this list involves a probability rather than a certainty, and each of those probabilities is derived from a model, and each of those models depends on measurements that could be improved. The honest position is that the numbers in the rest of this list are the best available estimates rather than settled facts, and that some of them will change. The Andromeda result is the demonstration that this is not a hedge. It is how the field actually works, and it is why a theory being unsettled is not the same thing as a theory being wrong. If a measurement of one nearby galaxy could unsettle a prediction that large, it is worth asking how well anyone can predict the motions of the 8 objects closest to us. Number 8. The solar system is not a clock. Isaac Newton believed the solar system was unstable, and said so in print. In the optics, he suggested that the mutual gravitational pull of the planets on one another would gradually derange their orbits, and that divine intervention would eventually be required to set things right. It was not a throwaway line. It was the considered opinion of the man who had just written down the law of gravitation, and it followed from an honest assessment of what his own equations could and could not guarantee. Pierre-Simon Laplace considered this an embarrassment to the mathematics and spent a large part of his career eliminating it. Working with Joseph-Louis Lagrange and using the technique now called perturbation theory, he showed that to first order, the planet's orbital elements oscillate rather than drift. The eccentricities and inclinations wobble within bounded ranges, and the semi-major axes, the sizes of the orbits, show no secular change at all. Laplace announced that the solar system was stable, that no divine correction was needed, and the matter was considered closed for the better part of a century. It was reopened by a prize competition. In 1889, King Oscar II of Sweden offered an award for progress on the N-body problem, given a system of bodies attracting each other by gravity, described their motion for all time. Henri Poincaré submitted an entry on a restricted version of the three-body problem and won. The paper was accepted, typeset, and printed. While copies were being distributed, the journal's editor, Lars Edvard Fragmen, wrote to Poincaré about a passage he could not follow. Poincaré investigated. There was an error, and correcting it destroyed his result. But the correction revealed something considerably more interesting than the theorem he had lost. He paid, out of his own pocket, to have the printed copies recalled and destroyed. The cost exceeded the prize money, and rewrote the memoir from scratch. What he had found was that the trajectories in the three-body problem can weave into an infinitely complicated structure, now called a homoclinic tangle, in which paths that begin arbitrarily close together diverge without bound. Poincaré wrote that the figure was so complex he would not even attempt to draw it. He had discovered deterministic chaos 70 years before the term existed and 80 before anyone had a computer capable of showing what it looked like. Deterministic chaos is a specific and frequently misunderstood thing. It does not mean random. The equations are exact, and the future is fully determined by the present. What it means is that the sensitivity to initial conditions grows exponentially, so that any uncertainty in the starting state, and there is always uncertainty because measurements have finite precision, expands until the prediction is worthless. Determinism and predictability are not the same property, and the solar system has the first without the second. The modern quantitative answer came from Jacques Lascar. In 1989, in Nature, Lascar published a numerical integration of the solar system's secular equations spanning 200 million years. He found the inner solar system to be chaotic, with a Lyapunov time of about 5 million years. That number deserves unpacking because it is the single most important figure in this entry. The Lyapunov time is the interval over which a small uncertainty grows by a factor of e, roughly 2.7. 5 million years means that uncertainties grow by a factor of about 10 every 10 million years. Follow that through. An error of 15 meters in Earth's position today becomes an error of 150 meters in 10 million years, a kilometer and a half in 20, and so on, until at about 100 million years, the error is 150 million kilometers, a full astronomical unit, the entire distance from the Earth to the Sun. The practical consequence is a hard horizon on prediction. Beyond roughly 60 million years into the future, the positions of the inner planets along their orbits are not calculable, and no improvement in measurement fixes it. To predict 100 million years ahead, you would need to know the current positions to a precision far beyond anything physically meaningful. The horizon works backward too. Astronomical dating of sedimentary layers by orbital cycles, which is one of the most precise tools in geology, becomes unreliable past about the same interval into the past. But chaotic is not the same as catastrophic. A chaotic system can wander unpredictably while remaining confined to a bounded region. The planets could shuffle their positions along their orbits indefinitely, without anything dramatic happening. The question Lascar's result raised, and did not answer, was whether the chaos has a violent branch. He and Michael Gastineau answered it in Nature in 2009, and the method is worth describing because it is unusual. They could not predict the solar system's future. So instead of predicting it, they sampled it. They ran 2,501 complete numerical integrations of the entire solar system over 5 billion years, the remaining main sequence lifetime of the Sun. Each run was identical except for one thing. The initial position of Mercury was shifted by less than a meter relative to the others, spread across the runs in increments smaller than any plausible measurement error. Since chaos guarantees those runs diverge, the ensemble maps out the range of futures consistent with what we actually know. In about 99% of the runs, nothing much happens. The planets shuffle, the eccentricities wobble, and the architecture holds for 5 billion years. In about 1%, it does not. The mechanism in those runs is a resonance, and it involves the two ends of the planetary system talking to each other. Every planet's orbit is an ellipse whose long axis slowly rotates. The perihelion precesses. Mercury's precesses at one rate, Jupiter's at another. These rates are labeled in the technical literature as G1 for Mercury and G5 for Jupiter. Ordinarily, they differ, and the small tugs the two planets exert on each other average out over time. But the rates are not fixed. They drift slightly as the whole system evolves. If G1 and G5 drift into agreement, the tugs stop averaging out and start adding up, cycle after cycle, and Jupiter, by far the most massive planet, more than twice everything else combined, begins pumping energy into Mercury's orbit. Mercury is already the most eccentric planet in the system, with an orbital eccentricity of about 0.206. That carries it from 46 million kilometers from the Sun at perihelion out to about 70 million at aphelion, a 50% swing. It is also the least massive planet and the closest to the resonance condition. In the runs where things go wrong, its eccentricity climbs past 0.5, then past 0.7, and at that point the orbit crosses Venus's. Run the model forward and watch Mercury. For the first 100 million years, nothing appears to happen. The orbit is where it has always been, a small tight ring near the Sun, tilted 7 degrees to the plane of the others. The perihelion swings slowly around, one full circuit every 230,000 years or so, and the eccentricity breathes in and out in cycles of a few 100,000 years, the way it has for 4.5 billion. Then, in this particular run, the breathing stops, returning to where it started. Each cycle, the eccentricity comes back a fraction of a percent higher than the last. It is not visible at any single moment. You could watch for 10 million years and be unsure whether anything was happening at all. But the fraction compounds, and compounding over 1 billion years is a different proposition from compounding over 1 million. The ellipse lengthens. The perihelion draws closer to the Sun, and the aphelion pushes outward, and the innermost planet is no longer sitting on a small, tight ring. Watch long enough, and Mercury's aphelion reaches the orbit of Venus. Now the two planets are on crossing paths, and their close approaches begin to dominate the dynamics entirely. The outcomes at that point are various, and none of them are gentle. In some runs, Mercury's orbit shrinks until it falls into the Sun. In others, it collides with Venus at tens of kilometers per second. In 18 of the 2,501 runs, the disruption propagates outward. Venus and Earth's orbits are destabilized by the loss of the resonance structure that had been holding them, and Mars is thrown onto a crossing orbit. In one specific solution, Lascar and Gastineau followed in detail, Mars collides with Earth about 3.3 billion years from now. In another, a close encounter between Venus and Earth wrecks both orbits without an impact. 1% over 5 billion years. That is the headline number, and there is a detail attached to it that most people find surprising. Lascar also ran the calculation with general relativity switched off, using purely Newtonian gravity. The probability of Mercury destabilizing rose to about 60%. General relativity is what stabilizes the solar system. The relativistic correction to Mercury's perihelion precession, the famous 43 arcseconds per century that Newtonian gravity could not account for, and that Einstein explained in 1915 as the first successful test of his theory, shifts G1 just far enough away from G5 to make the resonance hard to reach. The single measurement that confirmed general relativity is also the effect that keeps the inner solar system in one piece. Without it, on this evidence, we would be living in a system with a better than even chance of tearing itself apart before the sun dies. Konstantin Batygin and Gregory Laughlin published an independent analysis in 2008 using different numerical methods and reached compatible conclusions. Later work has refined the probability in both directions without removing it. The current honest scientific position is that the inner solar system has something on the order of a 1% chance of a serious instability before the sun leaves the main sequence, that the mechanism is understood, and that there is no calculation which can tell us which branch we are on, because the required precision does not exist and cannot be obtained. A few things put that 1% in context. The outer solar system is far more stable than the inner one. Jupiter, Saturn, Uranus, and Neptune have Lyapunov times of tens of millions of years and no realistic destabilization path over the Sun's remaining lifetime. Their orbits are widely separated relative to their masses, and Jupiter's dominance means the others are more governed than governing. The chaos lives among the four small inner planets, which are close together, low in mass, and sensitive to being pushed. There is also a smaller, entirely survivable version of the same physics operating right now, and it has left a clear mark on this planet. Earth's orbital eccentricity varies between roughly 0 and 0.06 on cycles of about 100,000 and 400,000 years. Its axial tilt oscillates between about 22.1 and 24.5 degrees on a 41,000-year cycle. The direction of the tilt precesses on a cycle of about 26,000 years. These are the Milankovitch cycles, worked out by Milutin Milankovitch in the 1920s, and the pattern they produce in the distribution of sunlight across latitudes and seasons is what paces the ice ages. They are visible in ocean sediment cores, in ice cores, and in layered rock hundreds of millions of years old. The planets moving each other around is not an abstraction. It is written into the rock record as alternating bands. It is also worth noting that the solar system has already been rearranged at least once. The NICE model, developed by a group working in Nice in the mid-2000s, proposes that the giant planets formed in a much more compact configuration and migrated outward through interactions with a disk of leftover planetesimals, passing through a resonance that destabilized the whole outer system and scattered debris throughout the inner solar system. Some versions of the model include a fifth giant planet that was ejected entirely during the rearrangement and is presumably still traveling somewhere as a rogue world. The evidence for the migration is indirect but substantial. The orbital structure of the Kuiper belt, the capture of Jupiter's Trojan asteroids, and the distribution of ages in lunar impact basins. So the architecture of this system is not an original design. It is the current output of a process, and the process is still running. The computational effort behind these results deserves a mention because it explains why nobody answered the question earlier. Lascar and Gastineau's 2009 study required integrating the full equations of motion for the solar system, including relativistic corrections and the Moon, across 5 billion years, 2,501 separate times. That is a step size measured in days across a span of billions of years, repeated thousands of times over. It consumed months of time on a large computing cluster. Poincaré identified the problem in 1890. The tools to characterize it statistically arrived 120 years later. Mercury is an odd planet to have this responsibility, and a few of its other properties are worth knowing. It is the smallest planet, at about 38% of Earth's diameter, and it is the densest after Earth once you correct for compression. Its iron core occupies something like 85% of its radius, which is an extraordinary proportion and still not fully explained. It is locked in a 3-to-2 spin-orbit resonance, rotating exactly 3 times for every 2 orbits, which means a solar day on Mercury lasts 2 Mercurian years. It has no atmosphere to speak of, and a surface that swings between about 430 degrees Celsius in sunlight and minus 180 in shadow. And despite being the closest planet to the Sun, it holds water ice in permanently shadowed craters at its poles, confirmed by radar from Earth in the 1990s and by the Messenger spacecraft in 2012. None of that is why it destabilizes. It destabilizes because it is light, because it is close to the Sun where precession rates are fastest, and because its eccentricity is already high enough that it does not have far to go. There is one more technical point that makes the 2009 result more solid than it might sound. Earlier studies of solar system stability used simplified equations, averaged versions that strip out the fastest oscillations to make long integrations tractable. Lascar and Gastineau used the full equations, including general relativistic corrections, and the Moon treated as a separate body rather than lumped in with Earth. That matters because the Moon exerts a real influence on Earth's axial behavior and on the fine structure of the inner system's resonances. Simplified models had suggested instabilities before and had been dismissed on the grounds that the simplification might have introduced them. The full integration removed that objection. And the 1-meter shift used to seed the ensemble is worth appreciating for what it says about the problem. 1 meter is roughly the precision with which spacecraft ranging can locate a planet, which is to say, the very best anyone can do. The study did not use a sloppy uncertainty to manufacture divergence. It used the actual limit of human measurement, and the actual limit of human measurement is enough to produce futures that differ by whether a planet exists. What makes this entry belong on a list about warning time is that it has, in a sense, the strangest position on the list. The warning time is not short. If Mercury's eccentricity began climbing, it would be obvious in the numbers for hundreds of millions of years before anything happened, and any civilization with the ability to measure planetary positions would see it coming from an unimaginable distance. The problem is the opposite. We cannot tell whether it has already started. The eccentricity of Mercury's orbit today is 0.206. In the runs that end badly, the eccentricity at this stage of the process is also about 0.2. There is no measurement that distinguishes the 1% of futures from the 99%, because the distinguishing information is not in the present state at any precision we can achieve. It is in decimal places that do not exist. The thing that keeps this one interesting is not the probability, which is low, and not the time scale, which is irrelevant to anything living. It is the demolition of an assumption almost everybody carries without examining it, that the arrangement of the planets is a fixed background against which everything else happens. It is not a background. It is a solution to a set of equations that has more than one answer, and which answer we are in is not something the equations will say. Chaos among the planets is at least chaos among objects we can see. There is a serious argument, taken seriously by serious people, that most of the mass in this neighborhood is made of objects nobody can see at all. Number 7. Primordial black holes. Every black hole anyone has ever confirmed formed in one of two ways. Either a massive star ran out of fuel and its core collapsed, or something at the center of a galaxy grew over billions of years by swallowing gas and stars and other black holes. Those are the two entries in the catalogue, and they cover everything from the stellar mass objects LIGO detects to the monsters at the hearts of quasars. There is nothing in physics that requires this to be the complete list. A black hole is not a kind of object in the way that a star or a planet is a kind of object. It is a condition, a quantity of mass compressed inside a particular radius, the Schwarzschild radius, below which no configuration of matter can hold itself up against its own gravity. Stellar collapse is one way to reach that condition. It is not the only conceivable way. It is simply the only way available in the present-day universe, because nothing in the present-day universe is dense enough to do it by any other route. The early universe was different. In the first fraction of a second after the Big Bang, the density everywhere was so high that a region only slightly denser than its surroundings could satisfy the condition directly, without any star being involved at all. Yakov Zeldovich and Igor Novikov proposed this in 1967. Stephen Hawking developed it in 1971 in a paper for the monthly notices of the Royal Astronomical Society with the plain title Gravitationally Collapsed Objects of Very Low Mass. The idea has been in the literature for more than half a century, and for most of that time it was regarded as an interesting possibility with no supporting evidence. The mass of a primordial black hole is set by a simple relation. It is roughly the amount of matter inside the cosmological horizon at the moment it formed. The horizon grows with time, so earlier formation means smaller black holes. Form at 1/10,000th of a second after the beginning, and you get something around a solar mass. Form at 10 to the minus 23rd power seconds, and you get something with the mass of an asteroid. Form earlier still, and you get objects light enough to have already evaporated. That last category is where Hawking's original interest lay. Small black holes radiate strongly and evaporate quickly, ending in a burst of gamma radiation of about 10 to the 30th power ergs. Anything below roughly 10 to the 15th power grams, 100 billion kilograms, the mass of a large mountain, formed in the early universe, would have finished evaporating by now, and the final bursts should be detectable as a distinctive class of short gamma-ray event. Astronomers have looked. No such signal has ever been found, which places a limit on how many small primordial black holes were made. The asteroid mass window is where the argument lives now, and the reason it lives there is dark matter. Dark matter accounts for about 27% of the universe's total energy content, and about 85% of its matter. Its existence is inferred from a long list of independent observations, the rotation curves of spiral galaxies, which stay flat far beyond the visible disk where they should fall off, the velocities of galaxies within clusters, first noted by Fritz Zwicky in the Coma cluster in 1933, gravitational lensing, the separation of mass from gas in colliding clusters like the Bullet cluster, and the detailed pattern of fluctuations in the cosmic microwave background, which requires a component that clumps under gravity without interacting with light. For 50 years, the assumption has been that dark matter is a particle, something outside the standard model, produced in the early universe, filling every galaxy with a diffuse halo. Enormous effort has gone into finding it. Direct detection experiments have built increasingly sensitive detectors deep underground, where cosmic rays cannot reach, tanks of ultra-pure liquid xenon, monitored for the faint flash of a dark matter particle recoiling off a nucleus. Lux Zeppelin and Xenont have pushed the exclusion limits down by many orders of magnitude. The Large Hadron Collider has searched for supersymmetric partners, which would supply a natural candidate. Axion experiments continue with a different set of techniques entirely. None of them has found anything. That is not proof of absence, and most physicists still expect dark matter to be a particle. But the sustained failure has made people revisit older ideas, and the oldest alternative is that dark matter is not a new kind of matter at all. It is ordinary mass, compressed into objects that do not shine. The constraints on that idea have been closing from both directions for 40 years, and it is worth walking through them, because what survives is narrow and specific. From below, evaporation. Anything under about 10 to the 15th power grams is gone already, and the absence of the expected gamma-ray signature limits how many there were. From above, gravitational lensing. If a compact object passes almost exactly between us and a background star, its gravity acts as a lens, focusing the star's light, so the star appears to brighten and then fade over a period from hours to months, depending on the lens's mass. This is gravitational microlensing, and it does not care whether the lens emits any light of its own. Several large surveys have been running for decades, Macho, Eros, Ogle, monitoring millions of stars in the Magellanic Clouds and the galactic bulge, counting events. If dark matter were made of objects heavier than about 10 to the 28th power grams, roughly the mass of a small asteroid, those surveys would have seen far more events than they did. The most demanding constraint came from a single observation. Hiroko Niyakura and colleagues, publishing in 2019, used the Subaru telescope's Hyper-Suprime Cam to image the Andromeda Galaxy continuously for 7 hours, taking an exposure every 90 seconds and monitoring tens of millions of individual stars. Very small lenses produce very brief brightenings. A lens of asteroid mass produces an event lasting minutes rather than months, so a rapid cadence observation of an enormous number of stars is the only way to look for them. They found one candidate event out of tens of millions of stars, which is consistent with essentially nothing, and it closed a substantial part of the remaining window. What survives, after all of that, is a range from roughly 10 to the 17th to 10 to the 23rd power grams. That is asteroid mass, from about 100 billion tons up to about 100 trillion. Physically, such objects are absurdly small. A primordial black hole of 10 to the 20th power grams has a Schwarzschild radius of about 150 femtometers, which is smaller than an atomic nucleus. At the top of the window, they are still smaller than a grain of sand. Objects in that window can account for 100% of dark matter without violating any existing observation. Not a fraction of it. All of it. If that is the answer, then 85% of the matter in the universe is not made of anything. It is geometry, regions where space-time has closed over on itself, drifting through every galaxy in enormous numbers, interacting with everything else only through gravity, which is precisely the behavior dark matter is observed to have. The idea got a substantial jolt in 2015. On the 14th of September that year, the LIGO detectors recorded their first gravitational wave signal from the merger of two black holes about 1.3 billion light-years away. The event was catalogued as GW150914. The masses were about 36 and 29 times the mass of the Sun. That was heavier than expected. Stellar evolution models had generally predicted that black holes formed from massive stars in the local universe would cluster at lower masses because massive stars lose enormous amounts of material to stellar winds before they collapse, and the wind loss scales with metallicity. 36 solar masses required either a very metal-poor progenitor or something else. Simeon Bird and colleagues, and independently Misao Sasaki and collaborators, pointed out in 2016 that a primordial population would produce exactly this: black holes in the tens of solar masses, in binaries formed by chance capture rather than by stellar evolution, with randomly oriented and generally low spins. LIGO and Virgo have now catalogued well over 100 mergers, and the spin distribution has stayed broadly consistent with that prediction, though it is also consistent with several astrophysical formation channels. It is a hint, not a proof, and the people arguing both sides are careful about saying so. Then came the proposal that made headlines, and it concerns the solar system. Planet 9 is a hypothesis put forward by Konstantin Batygin and Michael Brown in 2016. A handful of distant trans-Neptunian objects, small bodies far beyond Neptune's orbit, have orbits that appear clustered in a way that random chance does not easily explain. Their proposed explanation was an undiscovered planet of 5 to 10 Earth masses on a long eccentric orbit somewhere between 400 and 800 astronomical units from the Sun, shepherding those objects gravitationally. In 2020, Jakob Schultz and James Unwin published a paper in Physical Review Letters titled "What if Planet 9 is a primordial black hole?" Their argument was simple and difficult to dismiss. The evidence for Planet 9 is entirely gravitational. Nothing about it requires a planet. A captured primordial black hole of the same mass produces the same gravitational signature, and the mass range invoked for Planet 9 sits inside the range where primordial black holes could plausibly exist. The solar system, passing through the galaxy for 4.5 billion years, would have had opportunities to capture such an object. A black hole of 5 Earth masses has a Schwarzschild radius of about 5 centimeters. Grapefruit-sized. Somewhere past 400 astronomical units, in permanent darkness, emitting essentially nothing, invisible to every survey ever conducted, holding the orbits of a dozen distant ice balls in place. The paper is not a claim that this is the case. It is a demonstration that the observation does not distinguish between the two, and a proposal for how to tell them apart. Their suggested test is annihilation. Dark matter, if it is also partly particulate, would accumulate in a dense halo around such an object and annihilate at a low but steady rate, producing a faint gamma-ray point source with a distinctive spectrum. Searching archival gamma-ray data for such sources moving slowly against the background stars is a real observational program, and it has been attempted without a detection. Edward Witten proposed a different approach in 2020. Send a swarm of very small, very light spacecraft outward in many directions, and track their trajectories precisely enough to detect the anomalous gravitational tug of an unseen mass. It is technically plausible, and nobody has funded it. The more likely resolution is simpler. The Vera C. Rubin Observatory in Chile, which began survey operations in 2025, will image the entire visible sky every few nights with a 3.2 gigapixel camera. If Planet 9 is a planet, it reflects sunlight, and Rubin will find it as a slowly moving point of light, probably within the first few years of the survey. If Rubin completes its 10-year survey and finds nothing, then either the clustering has a different explanation or the object is there and does not reflect light, and the second possibility becomes considerably harder to wave away. There is another line of investigation worth mentioning, because it is genuinely strange. Earl Bellinger and colleagues examined, in 2023, what happens to a star that forms around a primordial black hole, or captures one into its core. They called them Hawking stars. The black hole slowly accretes from the stellar interior, while the star continues to fuse normally around it. And for a wide range of parameters, the star survives for billions of years, looking almost but not quite like an ordinary star. The differences are subtle and appear in asteroseismology, the study of the oscillation modes that ripple through a star's interior, which are sensitive to the density profile near the center. The Sun has been measured that way extremely precisely. The Sun does not have one. But the paper raises the possibility that some fraction of the stars in the sky are hollow in a very literal sense, and that the only way to find out is to listen to them ring. What earns this entry its place is not that a primordial black hole is likely to arrive. It is not. The estimated rate at which an object in the relevant mass range would pass through the inner solar system is less than once in the entire age of the solar system, and even if one did, a body of asteroid mass and nuclear size passing through at typical galactic velocities would produce a gravitational perturbation and very little else. What earns it a place is the implication. There is a question that any careful listener should be asking at this point, which is where the density fluctuations came from in the first place. The standard answer is inflation. In the leading model of the very early universe, a brief period of exponential expansion stretched quantum fluctuations, the unavoidable jitter of quantum fields, up to macroscopic scales, seeding the density variations that later grew into galaxies. Those fluctuations are directly measured. They appear as the tiny temperature variations in the cosmic microwave background, about 1 part in 100,000, and their statistical pattern matches inflation's prediction remarkably well. 1 part in 100,000 is far too small to collapse a region into a black hole. To make primordial black holes, you need fluctuations of order 1, a region roughly twice as dense as its surroundings, at some particular scale. The measured fluctuations at the scales cosmology can see are nowhere near that. But cosmology can only see certain scales. The cosmic microwave background probes fluctuations on scales corresponding to the size of galaxy clusters and larger. Much smaller scales, corresponding to the horizon size at very early times, are essentially unconstrained by any observation, and a wide range of otherwise reasonable inflation models produce a spike in the fluctuation spectrum at exactly those scales. So the honest position is that primordial black holes are neither required by inflation nor excluded by it, and that the parameter that decides the question is one nobody has measured. There is also a constraint from the cosmic microwave background itself that closes the upper end of the mass range further. A large primordial black hole existing before recombination would accrete surrounding gas, and accretion releases energy, and injected energy distorts the background spectrum and its polarization pattern in ways that are precisely measured. Those measurements rule out heavy primordial black holes as a dominant dark matter component, which is part of why the asteroid mass window is the only one left standing. A word on Hawking temperature, because it produces an odd fact. A black hole's temperature is inversely proportional to its mass, so small black holes are hot. An asteroid mass primordial black hole has a Hawking temperature in the billions of Kelvin. That sounds like it should make them conspicuous. It does not, because the emitting area is the area of the event horizon, and the event horizon in this case is smaller than an atomic nucleus. A surface of that size radiates almost nothing regardless of how hot it is. The total power output of a 10 to the 20th power gram black hole is a tiny fraction of a watt, spread across a sphere the size of the galaxy. That is the whole reason these objects can be everywhere and invisible simultaneously. And the question people always ask, what if one hit something? The honest answer is anticlimactic. An object of asteroid mass and nuclear size, moving at a couple of 100 kilometers per second, would pass through a planet essentially without interacting. It would gravitationally attract material along its path, and the material would not have time to fall very far before the object was gone. Estimates of the energy deposited by such a passage through the Earth range from negligible to a modest seismic signal. Some groups have proposed searching seismometer archives for the characteristic signature of a straight-line transit, a compression wave arriving at stations in a specific geometric sequence, and nothing has been found. The consequences of this idea are not local. They are inventory consequences. If primordial black holes are dark matter, then the Milky Way's halo contains something like 10 to the 25th of them, and the nearest one is probably somewhere inside the orbit of Neptune right now, and there is no instrument on Earth or in space capable of confirming or denying that sentence. For a century, the assumption underlying every survey has been that the universe is made of things that interact, things that emit, absorb, reflect or block light, and that can therefore be catalogued. Dark matter already violated that assumption, and the response was to assume it is a particle we have not yet detected, which preserves the idea that it is a kind of stuff. The primordial black hole hypothesis does not preserve that idea. It says the missing 85% may not be stuff at all. It may be a very large number of very small holes formed before the first second was over, drifting through every galaxy, permanently outside the reach of any instrument that works by detecting light. And the honest summary of the current situation is that we cannot rule it out, that the open mass window is real, that the objects would be undetectable by every method currently deployed, and that the single most likely place to settle the question in the next decade is not a particle detector in a mine. It is a telescope in Chile looking for a planet. There is one more thing hiding at the outer edge of the solar system that people have searched for very hard, over decades, using the best instruments available in each generation. The reason they searched is a rhythm somebody found in the fossil record. Number 6. The clock in the fossil record. In 1984, two paleontologists at the University of Chicago published a paper in the Proceedings of the National Academy of Sciences that has never stopped causing arguments. Their names were David Raup and John Sepkoski. Sepkoski had spent the better part of 2 decades on a project that most of his colleagues regarded as clerical rather than scientific. He was assembling a compendium of marine animal genera through geological time. For every genus in the fossil record, the stratigraphic interval in which it first appears and the interval in which it last appears. 36,000 of them, entered by hand, drawn from the scattered literature of a century and a half of paleontology, published in installments. It was the most complete database of its kind that had ever existed, and it took a career. Raup took that database and ran a time series analysis on the extinction rate over the last 250 million years, asking a straightforward statistical question: is the pattern of extinction random? It was not. The analysis showed a periodicity of about 26 million years. Extinction rates rose and fell on a rhythm, and the rhythm was regular enough to be detected across dozens of geological stages. The timing of that finding matters. 4 years earlier, in 1980, Luis Alvarez, his son Walter, and colleagues had published their proposal that the extinction at the end of the Cretaceous was caused by an asteroid impact. Their evidence was an anomalous concentration of iridium, an element rare in Earth's crust and common in meteorites, in a thin clay layer at the boundary, found first at Gubbio in Italy and then at boundary sections worldwide. The hypothesis was controversial for a decade and then vindicated in 1991 when the Chicxulub crater was identified beneath the Yucatan Peninsula, a buried impact structure about 180 kilometers across, dated to precisely the right moment, formed by an object roughly 10 to 15 kilometers in diameter, arriving at something like 20 kilometers per second and releasing energy on the order of 100 million megatons. So by 1984, impacts were respectable. And a periodic pattern of extinctions with impacts as the mechanism demanded a clock, because nothing on Earth keeps time on a 26 million year cycle. Plate tectonics does not. Volcanism does not. Sea level does not. Only orbits keep time that well. Two proposals appeared in the same issue of Nature, side by side, in 1984. Daniel Whitmire and Albert Jackson published one. Mark Davis, Pete Hutt, and Richard Muller published the other. They had arrived independently at the same idea. The Sun, they proposed, has a companion. Not a bright one, a red dwarf or a brown dwarf, dim enough to have escaped every catalogue, on a highly eccentric orbit with a period of about 26 million years, reaching perhaps 1.5 light-years at its farthest point. At its closest approach, it would pass through the Oort cloud, the vast, roughly spherical reservoir of icy bodies that surrounds the solar system out to something like 100,000 astronomical units. A star passing through that reservoir would gravitationally scatter a fraction of the comets inward, and over the following million years or so, the inner solar system would experience a sustained shower of long-period comets, some of which would strike planets. Muller's group named it Nemesis. The name has done more work than the hypothesis. It is worth pausing on what the Oort cloud actually is, because it is the least directly observed major structure in the solar system. Nobody has ever seen it. Its existence is inferred entirely from the orbits of long-period comets, which arrive from every direction rather than from the plane of the planets, and whose orbital energies cluster in a way that implies a source at enormous distance. Ernst Öpik proposed such a reservoir in 1932, and Jan Oort worked out the modern version in 1950 from a careful analysis of 19 comet orbits. Every estimate of its population, commonly quoted in the trillions of objects, is an extrapolation. It is a structure we are confident exists and have never detected. The nearest edge of it may begin somewhere around 2,000 astronomical units. The outer edge may reach a quarter of the way to the nearest star. Comets from it take millions of years to fall inward, which means that any comet arriving today was dislodged by something that happened before there were modern humans, and the event that dislodged it is not recoverable from the comet's orbit. The Oort cloud is, in effect, a delay line. Whatever disturbs it sends its message a very long time later. So the search for Nemesis began, and it ran for 30 years. Searching for a cool, dim object anywhere in a full sphere around the Sun is a problem of infrared astronomy. A brown dwarf emits very little visible light and most of its output in the infrared, so the way to find one is to survey the entire sky at those wavelengths and look for something with a large parallax, an object that appears to shift position as Earth moves around the Sun, which is the signature of being nearby. Several generations of instruments made the attempt. The definitive answer came from the Wide Field Infrared Survey Explorer, WISE, which surveyed the entire sky in 4 infrared bands beginning in 2010. In 2014, Kevin Luhman published the analysis of what the survey could exclude. No object the size of Saturn out to 10,000 astronomical units. No object the size of Jupiter out to 26,000 astronomical units. A brown dwarf at 1.5 light-years, roughly 95,000 astronomical units, would have been vastly brighter than either of those limits and completely unmissable. Nemesis does not exist. The hypothesis is not disputed or contested, it is closed. The signal in the fossil record did not close with it. Adrian Mellott and Richard Bambach reanalyzed the extinction data in 2010 using geological timescales that had been substantially revised and improved since 1984, a crucial point, because a periodicity analysis is only as good as the dates underneath it, and one of the standing criticisms of Raup and Sepkoski's result was that the old timescale might be manufacturing the signal. Better dates should have degraded a spurious periodicity. They strengthened it. Mellott and Bambach found a clear periodicity of about 27 million years, detectable across 500 million years of record, twice the interval the original study examined, with a statistical significance higher than the original result. Michael Rampino, Ken Caldera, and Yuhong Zhu published a further analysis in 2020 and found a 27.5 million year pulse, and found it not only in extinction rates, but, separately, in the ages of large impact craters and in the timing of flood basalt eruptions, the enormous volcanic outpourings associated with several major extinctions. 3 different kinds of catastrophe, apparently sharing a rhythm. So the search moved from a companion star to something considerably more exotic. The Sun does not travel around the galactic center in a flat circle. It bobs, oscillating vertically through the galactic plane like a horse on a carousel, driven by the gravitational pull of the disk itself. The full vertical period is roughly 60 to 70 million years, which means the Sun crosses the midplane of the galaxy about every 30 million years, twice per oscillation. That number is tantalizingly close to 27, and people noticed it decades ago. The difficulty has always been the mechanism. The ordinary matter concentrated near the galactic plane is too diffuse to perturb the Oort cloud measurably during a crossing. Lisa Randall and Matthew Rees proposed a solution in Physical Review Letters in 2014 in a paper titled Dark Matter as a Trigger for Periodic Comet Impacts. Their suggestion was that a fraction of dark matter, a small subcomponent, not the bulk, might be dissipative. Ordinary dark matter is assumed to be collisionless, which is why it forms a puffy spherical halo rather than a disk. But if some fraction of it can radiate energy through an interaction of its own, that fraction would cool, lose energy, and settle into a thin, dense disk in the galactic midplane, exactly as ordinary matter does. A thin, dark disk would be dense enough to matter. Each time the Sun passes through it, the tidal field would jostle the Oort cloud strongly enough to trigger a comet shower, and the timing would follow the crossing period. It is a proposal with a real prediction attached. A dark disk would slightly alter the vertical motion of stars near the plane, and Gaia's astrometry is precise enough to test it. The tests so far have not found a dark disk, and the constraints are tightening. The idea is not dead, but it is not thriving. There is a serious counter-argument, and honesty requires giving it room. Corinne Baylor-Jones has argued, in a series of papers, that the periodicity is largely an artifact of how the geological timescale is constructed. Geological stages are not arbitrary divisions of time. Their boundaries are drawn where the fossil assemblages change, which is to say, at extinctions. If the boundaries are placed at extinctions, and the analysis bins the data by stage, then some degree of apparent regularity is built into the data before any analysis begins. Baylor-Jones has also pointed out that the statistical methods used in several of these studies are prone to finding periodicities in records that are merely clustered. That criticism has not been fully resolved, and it should temper anyone's confidence. The most defensible summary of the current state is this. A periodic signal of roughly 26 to 28 million years keeps appearing in extinction data, in crater ages and in volcanic records, using different datasets and different methods, over 4 decades. There is a substantial statistical critique of it, and every astronomical mechanism proposed to explain it has either been ruled out or failed to find supporting evidence. Which leaves the strangest possible position. There appears to be a clock, and nobody has been able to find anything doing the timekeeping. It helps to have the actual inventory in mind, because the phrase mass extinction gets used loosely, and the real events are not interchangeable. Paleontologists conventionally recognize 5. The end Ordovician, about 445 million years ago, removed roughly 85% of species and is the second most severe on record. The late Devonian, around 372 to 359 million years ago, was less a single event than a prolonged series of pulses. The end Permian, about 252 million years ago, is the worst, something like 96% of marine species, and is generally attributed to the Siberian Traps, an eruption that covered an area larger than Western Europe in basalt. The End Triassic, about 201 million years ago, coincides with the Central Atlantic Magmatic Province and cleared the way for the dinosaurs. And the End Cretaceous, 66 million years ago, which is the one everyone knows. Notice that 2 of the 5 are firmly tied to enormous volcanic events, 1 to an impact and 2 remain contested. That mixture is exactly why the periodicity argument is hard to settle. If a single mechanism were responsible for all of them, a single clock would be a natural explanation. Instead, there are at least 2 mechanisms, and the 2020 analysis by Rampino and colleagues found the same 27.5 million year rhythm in both impact craters and flood basalts, which either means one driver is somehow producing both or means the rhythm is in the dating rather than in the events. Michael Rampino's proposal, which he has called the Shiva hypothesis, attempts the first option. His argument is that a large impact does not only excavate a crater, it delivers an enormous shock into the mantle, and in some models the antipodal focusing of that shock can trigger or accelerate mantle plume activity on the opposite side of the planet. If that is right, then impacts and flood basalts are not independent phenomena, but 2 consequences of the same events, and a single astronomical clock could drive both. The mechanism is not widely accepted, and the timing correlations are approximate. There is also a second, longer cycle in the data that nobody talks about much, and it is stranger than the first. Robert Rohde and Richard Muller published an analysis in Nature in 2005 of marine biodiversity across the entire Phanerozoic, the last 542 million years, and found a strong periodicity of about 62 million years in the total diversity of marine genera, not merely in extinctions. Diversity rises and falls on that cycle with a consistency that is difficult to attribute to sampling. The authors were explicit that they had no explanation. 20 years later, there is still no accepted one, and the candidate explanations range from galactic-scale astronomy to long-period cycles in ocean chemistry and sea level. The natural question is where the present moment sits in any of these cycles, and the honest answer is that the question does not have a well-defined answer. If there is a 27 million year clock, then the 66 million years since the last major extinction spans about 2.5 cycles, which means at least 2 peaks have passed since the end of the Cretaceous without producing a mass extinction. That is either evidence that the clock is not real, or evidence that a peak in the cycle raises the probability of a large impact without guaranteeing one. There is a middling event in roughly the right place, the Eocene-Oligocene transition, about 34 million years ago, associated with substantial cooling and with 2 large impact craters, Popigai in Siberia at 100 kilometers across and Chesapeake Bay at 85, both dated to around 35 million years ago. Whether that counts as a peak is a matter of interpretation. Planet 9, which came up at number 7, is worth separating cleanly from Nemesis because the 2 get conflated constantly. Nemesis was a stellar companion at 95,000 astronomical units, invoked to explain a fossil rhythm, and it has been ruled out. Planet 9 is a 5 to 10 Earth mass object at 400 to 800 astronomical units, invoked to explain the clustering of a handful of distant orbits, and it remains an open question. They are different objects, in different places, proposed for different reasons, and the failure of the first says nothing about the second. What makes this entry genuinely uncomfortable is not the prospect of a comet shower. It is the epistemics again, in a new form. At number 9, a solid prediction moved because a nearby measurement improved. Here, the situation is the reverse. The measurement has improved repeatedly over 40 years, and the signal has become clearer each time, and the explanation has become less available each time. Every astronomical mechanism that would produce a rhythm on this timescale has been searched for with the best instrument of its generation, and not found. The dark disk is constrained. The companion star is excluded. The galactic plane crossings are real but too weak. And yet the pattern persists in the data, which means either that 4 decades of statistical work by multiple independent groups is being fooled by a subtle artifact of geological dating, or that something is keeping time and we have not identified it. That is worth naming, because the phrase comes back later on this list under very different circumstances. A clock nobody set. A rhythm in the record with no mechanism attached, ticking on an interval 100,000 times longer than a human life. Sepkoski died in 1999 at the age of 50. He had spent 2 decades typing fossil ranges into a database, 1 line at a time, in an era when computers were scarce and the work was regarded as bookkeeping. What he and Raup found in that database was not something either of them went looking for. It was a rhythm in the record of death, on a timescale so long that the entire history of primates fits inside a fraction of 1 cycle. 40 years later, better data has made the rhythm clearer and made every explanation for it worse. The signal has outlived the man who found it, and every mechanism anyone proposed to account for it, and it is still there. This is a good place to stop and look back at where this list has traveled. We began at 10 to the 100th power years and beyond, with the heat death, an ending so distant that the word warning has no meaning attached to it. We came down to 100 billion years, and the loss of the evidence. Then to 1 billion, and the end of this planet's ability to feed anything. Then to 4 billion, and a galaxy that may or may not arrive. Then to the chaos among the planets, which operates on hundreds of millions of years and which nobody can resolve. Then to the primordial black holes, which have no timescale at all, only a population. And now we are at tens of millions of years, and something has changed. Everything from this point down is not a prediction about the deep future. It is a description of something Earth has already experienced, more than once within the span of the fossil record. The remaining entries on this list have all happened before. The next one has the clearest evidence of any of them, because it is not inferred from a statistical pattern or a numerical model. It is sitting in the ocean floor, and it can be measured directly. Number 5. The shield has failed before. The sun does not sit in a vacuum. It sits inside a bubble of its own making, and the bubble is the reason this solar system is habitable in a way that has nothing to do with the habitable zone. The solar wind is a continuous outflow of charged particles, protons and electrons mostly, leaving the sun's corona at between 400 and 800 kilometers per second and carrying away roughly 1 million tons of the sun every second. It is not a trivial breeze. It carries the sun's magnetic field outward with it, wound into a spiral by the star's rotation, and it pushes against the interstellar medium that fills the space between the stars. Where the outward pressure of the wind balances the inward pressure of the interstellar gas, a boundary forms. Inside that boundary is the heliosphere, a cavity in the interstellar medium, filled with the sun's own plasma and threaded by the sun's own magnetic field. The heliosphere does one thing that matters enormously. Galactic cosmic rays, high-energy charged particles accelerated by supernova remnants and other violent processes throughout the galaxy, travel through interstellar space in enormous numbers. When they encounter the heliosphere's magnetic field, the lower energy ones are deflected. A substantial fraction of the galactic cosmic ray flux never reaches the inner solar system at all. Earth's own magnetic field and its atmosphere handle much of the rest. We know the shape of the heliosphere with unusual confidence because 2 spacecraft have flown out of it and reported back. Voyager 1 crossed the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic as it begins to feel the pressure of the interstellar medium ahead, on the 16th of December, 2004, at 94 astronomical units from the Sun. It crossed the heliopause, the true outer boundary, on the 25th of August, 2012, at 121.6 astronomical units. The crossing was unambiguous in the data. The count of particles originating from the Sun dropped sharply, the count of galactic cosmic rays jumped, and the plasma density rose by a factor of about 40, from roughly 2/1000ths of an electron per cubic centimeter to about 8/100ths. Voyager 2 crossed the heliopause on the 5th of November 2018 at 119 astronomical units, traveling in a substantially different direction. That second crossing was important. It confirmed that the boundary is real, that it is reasonably symmetric, and that the first measurement was not an artifact of one spacecraft's particular path. Both spacecraft are still transmitting, which is remarkable given that they launched in 1977 and were designed for a 4-year mission to Jupiter and Saturn. Their radioisotope thermoelectric generators lose about 4 watts of output per year, and instruments have been switched off one by one to keep the remaining ones alive. The plasma wave instrument on Voyager 1, which made the heliopause measurement, works by listening for the ringing of the surrounding plasma when a solar disturbance passes through it, a technique that requires the Sun to cooperate by producing an event, and then requires someone on Earth to be listening months later when the ringing arrives. Voyager 1 is now beyond 165 astronomical units, the most distant human-made object, and its signal takes more than 22 hours to reach Earth. Now, the important part. The heliosphere's size is not a fixed property of the Sun. It is a balance between 2 pressures. The solar wind pushes out, the interstellar medium pushes in. Change the interstellar medium and the balance moves, and the solar system does not stay in one place. The Sun is currently inside a structure called the local interstellar cloud, informally the local fluff. It is small, warm and extremely tenuous, roughly 30 light-years across, at a temperature around 7,000 Kelvin, with a density of about 0.3 atoms per cubic centimeter. For comparison, the best laboratory vacuums on Earth are far denser than that. The solar system entered it somewhere between 40,000 and 150,000 years ago, and will exit within a few tens of thousands of years, at which point it enters the next structure over, sometimes called the G-cloud. That cloud sits inside something much larger. The local bubble is a cavity roughly 1,000 light-years across, carved out of the interstellar medium and filled with gas so hot and so thin that it emits soft X-rays. It has been known since the 1970s, and its origin was worked out in detail by Catherine Zucker and colleagues in a paper in Nature in 2022. Their reconstruction used the 3-dimensional positions and motions of young stars and molecular clouds, made possible by Gaia's astrometry, to run the structure backward in time. The local bubble was excavated by roughly 15 supernovae over the past 14 million years. The expanding shell swept the interstellar gas outward, and the compressed gas at the shell's surface is where essentially all nearby star formation is now occurring. Every young stellar nursery within a few hundred light-years sits on the bubble's skin. And the Sun's position inside it is a coincidence. The solar system drifted into the cavity about 5 million years ago, on its own galactic orbit, unconnected to the events that created it. In June of 2024, Merav Ofer and colleagues published a paper in Nature Astronomy that took the next step and asked what happens when the Sun encounters something denser. Their reconstruction of the Sun's trajectory backward through the local interstellar environment indicated that about 2 million years ago, the solar system passed through a structure they call the local links of cold cloud, part of a ribbon of cold, dense neutral hydrogen clouds in this region of the galaxy. Cold clouds are far denser than the warm, tenuous gas the Sun currently occupies, by factors of hundreds or more. They modeled what that encounter would do to the heliosphere, and the answer was severe compression. In their strongest case, the heliosphere shrinks from its present 100+ astronomical units to inside 0.22 astronomical units, well inside the orbit of Mercury and far inside the orbit of Earth. If that is right, then for a period ranging from a few hundred years to as long as 1 million, Earth was not inside the heliosphere at all. The planet sat directly in the interstellar medium, exposed to the full galactic cosmic ray flux, and to a wind of neutral interstellar hydrogen and dust that had never been inside a star system. 2 million years ago, on an East African plain, an early member of our own genus looks up. The sky has been changing slowly for a very long time, on a timescale far too long for anyone to notice it changing. There has been no bang and no flash. Nothing has arrived. What has happened is that something has been taken away, and the taking has been gradual. The aurora is not where it should be. It is not confined to the far north. There are faint curtains and glows at latitudes where such things should never appear, night after night, in a slow green shimmer that has simply always been there as far as anyone in this landscape has ever known. The particle flux at the top of the atmosphere is higher than it has been in 1 million years. Interstellar dust that has never been near a star is drifting into the upper atmosphere, and some of it is settling, grain by grain, into the sediments that will one day be drilled and measured. Nothing about this is an event. There is no moment when it begins, and no moment when it ends. It is a condition that lasts longer than our entire species has so far existed, and every generation born into it inherits it as the ordinary state of the sky, and the last generation to live under it will have no idea that something has come back. That is the strangest thing about this entry. The failure of the shield is not a catastrophe with a date. It is a slow environmental change that a civilization could live through without ever identifying it, and that a species without instruments could not identify at all. There is physical evidence that something happened around that time, and this is where the entry stops being a model and starts being a measurement. Iron 60 is a radioactive isotope of iron with a half-life of about 2.6 million years. It is produced in significant quantities in supernovae and in the winds of massive stars, and it has no meaningful terrestrial source. Any iron 60 present when the Earth formed decayed away billions of years ago. If you find iron 60 in a young geological deposit, it arrived recently from space. Klaus Knie and colleagues found it first, in 1999, and again in 2004, in a deep-sea ferromanganese crust from the Pacific, one of those slow-growing mineral layers that accumulate over millions of years and act as an archive of whatever was settling out of the ocean at the time. Anton Wollner and collaborators mapped it in far more detail in Nature in 2016, using samples from multiple ocean basins, and identified 2 distinct deposition pulses, one centered around 2.5 to 3 million years ago, and an older one near 6.5 million. Plutonium-244, another isotope with no terrestrial source, has been found alongside it. And in 2019, Wollner's group reported iron 60 in Antarctic snow that fell within the last 2 decades, which indicates that the solar system is still, right now, moving through material enriched by relatively recent nearby supernovae. The dating of those pulses is the part that makes people uncomfortable, and it is also the part that requires the most care. The 2.5 to 3 million year pulse falls close to the onset of the Pleistocene glaciations, the beginning of the current cycle of ice ages. It also falls close to Ophir's proposed cloud passage and close to a period of significant change in African environments and in hominin evolution. Several papers have noted the coincidence and proposed a connection. Increased cosmic ray flux enhances the production of ions in the atmosphere. Ions may serve as nuclei for cloud droplet formation. More clouds mean higher albedo. Higher albedo means cooling. That chain of reasoning is not established. Each link is plausible, and none of them is demonstrated at the required strength, and the cloud nucleation step in particular has been tested repeatedly with mixed results. What can be said honestly is this: there are three things: a supernova signature in the sediments, a modeled heliosphere collapse, and a major climatic transition that fall within the same interval of a few 100,000 years, and that a mechanism connecting them can be sketched but not confirmed. Coincidence in timing is a reason to investigate, not a reason to conclude. What is not in question is the exposure itself. The iron 60 is measured. The half-life is known. The isotope has no terrestrial source. Material from at least one nearby supernova reached this planet's surface within the last 3 million years, and reached it in enough quantity to be detectable in ocean crusts, in lunar regolith samples returned by Apollo, and in fresh Antarctic snow. There is one further point worth making about the record, because it shows how much of this is preserved. Cosmic ray flux at the top of the atmosphere controls the production rate of certain isotopes, carbon-14, produced when cosmic ray secondaries strike nitrogen, and beryllium-10, produced by spallation of atmospheric nitrogen and oxygen. Carbon-14 is taken up by plants and ends up in tree rings. Beryllium-10 settles out and ends up in ice cores. Both are measured with high precision, and both therefore preserve a partial record of how well shielded this planet has been, year by year, going back tens of thousands of years in the case of tree rings and hundreds of thousands in the case of ice. That record becomes extremely important in the next entry but one, for a very different reason. The instrument that will settle much of this is already flying. The Interstellar Mapping and Acceleration Probe is designed to map the heliosphere's boundary at far higher resolution than its predecessor, using energetic neutral atoms, particles created at the boundary when a charged particle steals an electron from a neutral one and, no longer bound by the magnetic field, travels in a straight line back toward the inner solar system, carrying information about conditions where it was created. It is, in effect, a way to photograph the edge of the bubble from the inside. Some context on the interstellar medium itself is useful here, because most people have no mental picture of it at all, and the picture is genuinely strange. The space between the stars is not empty, and it is not uniform. It is sorted into phases, in the same way that water on Earth exists as ice, liquid, and vapor, except that the sorting is by temperature and density, and there are more than 3 categories. There is a cold, neutral medium, at perhaps 50 to 100 Kelvin, in clouds dense enough to block starlight. There is a warm, neutral medium, at several thousand Kelvin, which is what the Sun is currently in. There is a warm, ionized medium, and there is a hot, ionized medium, at 1,000,000 Kelvin or more, which is what fills the local bubble, gas so hot that it glows in X-rays, and so thin that the concept of temperature applied to it is almost misleading, because there are only a few thousand particles in a cubic meter. The solar system moves through this structure at about 26 kilometers per second, relative to the local gas, which works out to about 5.5 astronomical units per year, or roughly 1 light-year every 11,000 years. The Sun's orbit around the galactic center takes about 230 million years and carries it through spiral arms, through star-forming regions, and through whatever supernova remnants happen to be expanding at the time. Over the 4.5 billion years of the solar system's existence, it has completed something like 20 circuits and passed through an unknowable number of different environments. Estimates of how often the Sun encounters a dense cloud vary, but the general result is that encounters with cold clouds capable of significantly compressing the heliosphere happen on timescales of tens to hundreds of millions of years, and encounters with moderately denser gas happen far more often, possibly every few million years. Which means the current configuration is not the default. It is one of several states the solar system cycles through. The local interstellar cloud that surrounds us now is itself something of a puzzle. It is warm and partly ionized, and it should not survive long inside a bubble of million-degree gas. The hot surroundings should evaporate it. Various explanations have been proposed: that it is a fragment of the bubble's shell being pushed inward, that it is magnetically insulated, that it is younger than it looks. The Sun happening to occupy a small cloud whose existence is not fully explained, inside a large cavity created by supernovae that happened before there were humans, is the environment in which every observation in astronomy has ever been made. It is also worth noting how recently all of this became knowable. The local bubble's origin was reconstructed in 2022 because Gaia provided accurate three-dimensional positions and velocities for the young stars in this part of the galaxy, and that data did not exist before 2018. OFA's cloud passage result depends on the same astrometry. The Iron 60 measurements require accelerator mass spectrometry sensitive enough to count individual atoms in a sample where the isotope is present at a level of a few parts in 10 to the 16th. Every strand of the argument in this entry rests on instrumentation that is less than 3 decades old, and most of it less than 1. What earns this entry its position on the list is the reframing it forces. Most people, asked what protects life on Earth, will name the atmosphere and the magnetic field. Both are properties of this planet. Both are stable on any timescale that matters to a person. The heliosphere is not a property of this planet. It is a property of the Sun's relationship with whatever gas the solar system happens to be moving through, and the solar system is moving at about 230 kilometers per second around a galaxy whose interstellar medium is lumpy, structured, and constantly being rearranged by the deaths of stars. The shield is external, it is contingent, and the sediment record indicates that it has already been substantially reduced at least once while our ancestors were alive to stand underneath it. That same local bubble, the cavity that currently holds this solar system, the structure inside which all of this takes place, was carved out by the deaths of roughly 15 stars over 14 million years. Which is worth remembering, because the next question is what a star's death does at closer range. Number 4. The wandering black holes. The Milky Way contains something on the order of 100 million stellar mass black holes. That estimate is not controversial, and the way it is derived is straightforward. Take the initial mass function, the observed distribution of masses that stars are born with, which is well measured and appears to be roughly universal. Take the threshold above which a star ends its life as a black hole rather than a neutron star or a white dwarf, which is somewhere around 20 to 25 solar masses depending on metallicity and rotation. Integrate over the galaxy's star formation history, which is reasonably well constrained. The answer comes out in the range of 100 million to a few hundred million. Now the uncomfortable part. Until 2022, the number of isolated stellar mass black holes that had been directly confirmed was 0. Every black hole in the standard catalogue was found because it was interacting with something visible. Cygnus X1, identified as a black hole candidate in 1971, was found because it is stripping gas from a blue supergiant companion. The gas spirals in, heats to millions of degrees, and radiates X-rays. Sagittarius A star, the 4 million solar mass object at the center of the galaxy, was found by tracking the orbits of individual stars around an invisible mass over decades, the work of Reinhard Genzel's and Andrea Gheze's groups, which won the Nobel Prize in 2020. Merging black holes announce themselves in gravitational waves. Supermassive black holes in distant galaxies announce themselves as quasars. Every one of those detections requires the black hole to be doing something to something else. A black hole drifting alone through interstellar space is doing almost nothing. The interstellar medium is extraordinarily thin. In the local bubble, a few thousand particles per cubic meter. A stellar mass black hole moving through that at 100 kilometers per second accretes at a rate so low that the resulting emission is far below any detection threshold. It has no companion to strip, no disk to heat, no stars close enough to perturb measurably. It is a 30-kilometer sphere of absolute darkness, moving through a galaxy 100,000 light-years across, and there is no telescope in any band that can see it. There is exactly one method that works, and it is a strange one. Gravitational microlensing. If a massive, compact object passes almost precisely between us and a background star, its gravity bends the star's light around it, focusing it toward us. The background star appears to brighten smoothly, peak and fade again, over a period that depends on the lens's mass and velocity, hours for a planet, weeks to months for a stellar mass object. The effect requires no light from the lens whatsoever. It works on anything with mass. Surveys have been running for decades, monitoring millions of stars toward the galactic bulge where the density of background sources is highest. OGLE, the optical gravitational lensing experiment, operating from Chile since the early 1990s, detects thousands of microlensing events per year. MOA, Microlensing Observations in Astrophysics, operates from New Zealand. The problem is that a light curve alone does not give you the lens's mass. The event duration depends on mass, distance, and relative velocity together, and those three cannot be separated from the brightening alone. A long event might be a heavy nearby lens or a lighter, distant one moving slowly. To break the degeneracy, you need something else, the astrometric microlensing signal. As the lens passes, it does not only brighten the background star, it also shifts the star's apparent position by a tiny amount, because the two lensed images the object produces are unequal in brightness, so their combined centroid is displaced. That shift is on the order of a milliarcsecond, and measuring it requires the Hubble Space Telescope and a great deal of patience. In 2011, both OGLE and MOA detected an unusually long microlensing event toward the galactic bulge, catalogued as OGLE 2011 BLG 0462. The duration suggested a heavy lens. Kailash Sahu and colleagues began following it with Hubble, measuring the background star's position across repeated visits over 6 years. The technical difficulty is hard to overstate. The galactic bulge is one of the most crowded fields in the sky. The star being measured is blended with neighbors, and the shift being measured is smaller than a milliarcsecond, which is comparable to measuring the width of a human hair from a few hundred kilometers away. The result was published in 2022 and confirmed with additional Hubble epochs in 2025. A dark object of about 7.15 solar masses, roughly 5,000 light-years away, in the direction of Sagittarius, moving at about 45 kilometers per second, with no detectable light of any kind. It is the first, and, at the time of this recording, the only isolated stellar mass black hole confirmed by direct measurement. A competing analysis by Casey Lamb and Jessica Liu, using overlapping data, initially derived a lower mass, in the range where the object might be a neutron star rather than a black hole. The disagreement was resolved as more Hubble epochs accumulated and the higher mass held. It is worth knowing that the very first isolated black hole ever found spent 2 years being argued about. 11 years of work on one object out of an estimated 100 million. Gaia has since contributed detections of a different kind, and they are much closer to home. Gaia measures the positions of more than 1 billion stars repeatedly and with extraordinary precision, which means it can detect a star that is wobbling because something invisible is orbiting it. If the wobble implies a companion far too massive to be a dark star, the companion is a compact object. Gaia BH1, announced by Kareem El-Badri and colleagues in 2022, sits about 1,560 light-years away and weighs about 9.6 solar masses, orbited by an ordinary Sun-like star on a wide orbit of about 186 days. It is the nearest confirmed black hole to Earth. Gaia BH2, found shortly after, is around 3,800 light-years out, in a much wider orbit of about 3.5 years. Gaia BH3, announced in 2024, sits roughly 1,900 light-years away in the constellation Aquila and weighs about 33 solar masses, the most massive stellar black hole known in this galaxy, and one that appears to belong to an ancient, metal-poor population of stars swept up when the Milky Way absorbed a smaller galaxy long ago. All three were sitting in a catalogue of stellar positions, waiting for somebody to look for the right kind of wobble. Black holes also get thrown, and this is the part of the entry that produces the largest numbers. When two black holes merge, the gravitational waves they emit carry away momentum. If the merger is asymmetric, unequal masses or spins pointing in awkward directions, the emission is not balanced, and the remnant recoils in the opposite direction. For most configurations, the recoil is modest, a few hundred kilometers per second. For certain specific spin alignments, numerical relativity simulations produce what are called superkicks, reaching several thousand kilometers per second. Several thousand kilometers per second exceeds the escape velocity of any galaxy. A black hole receiving a superkick leaves permanently and spends the rest of the universe's history traveling through intergalactic space. There is a good candidate for this happening at the largest scale. The quasar 3C186, studied in detail by Marco Chiaberger and colleagues in 2017, shows an active nucleus, a supermassive black hole actively accreting, displaced roughly 35,000 light-years from the center of its host galaxy, and moving at over 2,000 kilometers per second relative to it. The most natural explanation is a recoiling supermassive black hole, kicked out of the galactic center by the merger of two black holes during a galaxy collision, dragging its accretion disk along with it. And in 2025 came a cleaner demonstration of the same idea, from a completely different direction. A tidal disruption event happens when a star wanders too close to a black hole and is pulled apart. The difference in gravitational force across the star's diameter exceeds the star's own self-gravity, and it is stretched into a stream of gas, roughly half of which falls back and forms a temporary accretion disk that flares brightly for months. These events are found regularly by wide-field surveys, and they almost always occur at the centers of galaxies, because that is where the supermassive black holes are. Yuhan Yao and colleagues reported an exception. The event catalogued as AT 2024 TVD occurred about 2,600 light-years from the center of its host galaxy, not at the nucleus. The black hole responsible weighs roughly 1 million solar masses. It is a supermassive black hole in the wrong place, and the only reason anyone knows it is there is that a star happened to wander close enough to be eaten while telescopes were watching. That is the pattern this entire entry is about. The objects announce themselves only when something else gets close enough, and the announcement is the last thing that happens to whatever got close. So consider the arithmetic of what that means for the population. If there are 100 million stellar mass black holes in this galaxy, distributed roughly like the stars themselves, then within any given volume, there should be roughly one black hole for every 1,000 or so stars. Within 100 light-years of the Sun, there are about 500 stars. The expected number of black holes in that volume is a fraction of 1, but the expected number within a few hundred light-years is not a fraction of 1, it is several. Nobody knows where they are. The nearest confirmed one is at 1,560 light-years, and it was found only because it happens to be orbiting a star bright enough for Gaia to measure. Statistically, the nearest one of any kind is probably closer than that by a substantial factor, and it will most likely never be found, because it is not doing anything. There is no survey that can fix this. Every other class of object in the galaxy can, in principle, be catalogued: stars by their light, planets by transits and radial velocity, brown dwarfs in the infrared, neutron stars by their pulses, molecular clouds by their absorption. Isolated black holes have no channel. They can be found by microlensing when they happen to pass in front of something, which is a matter of luck and geometry, and by nothing else. The situation will improve. The Nancy Grace Roman Space Telescope's microlensing survey, which will monitor an enormous number of bulge stars at high cadence with a wide field, is expected to detect on the order of 100,000 microlensing events and to yield the first statistically meaningful census of isolated compact objects, enough to test whether the 100 million estimate is right and to measure the mass distribution of the black holes that stars actually leave behind. There is also a gap in that distribution that nobody has explained. Between the heaviest stellar black holes, at a few tens of solar masses, and the lightest supermassive ones, at 100,000 or more, there is a range where almost nothing has been confirmed. Intermediate mass black holes should exist. They are the natural seeds for the supermassive ones, and yet the candidates are few and contested. The strongest is in the globular cluster Omega Centauri, where Maximilian Haberler and colleagues reported in Nature in 2024 that 7 fast-moving stars near the cluster's core are traveling quickly enough to escape and have not escaped, which requires at least 8,200 solar masses of unseen mass holding them in. And there is a related question about how black holes form at all that has an unsettling observational answer. Some massive stars, according to models, do not produce a bright supernova when they collapse. The core forms a black hole quickly enough that the explosion fails, and the star simply disappears. Surveys have been monitoring large numbers of massive stars for exactly this signature, and there is at least one strong candidate, a star in the galaxy NGC 6946, that was clearly present in images from 2009 and clearly absent in images from 2015, with a brief, modest brightening in between, and nothing since. A star with more than 20 times the Sun's mass went out, and nothing happened. The question everybody asks about this entry is what would happen if one came here, and it is worth answering carefully, because the honest answer is more interesting than the dramatic one. Picture a black hole of 10 solar masses entering the outer solar system at 100 kilometers per second, which is a typical relative velocity for objects in this part of the galaxy. Its event horizon is about 30 kilometers across, a sphere the size of a small city, absolutely black, with no atmosphere, no surface, and no light. At a distance of 1,000 astronomical units, it is doing nothing detectable. It exerts a gravitational pull 10 times the Sun's at that distance, which sounds significant until you note that at 1,000 astronomical units, the Sun's own pull is already negligible. It would perturb the outer Oort cloud, dislodging comets on a timescale of millions of years. Crossing into the planetary region, moving at 100 kilometers per second, it would traverse the distance from Neptune's orbit to the Sun in about 18 months. During that transit, it would substantially alter the orbits of whatever it passed near, by an amount depending entirely on how close it came. A pass at a few astronomical units from Earth would change Earth's orbit measurably and possibly severely. A pass at 50 astronomical units would rearrange the outer planets and leave the inner ones largely alone. Then it would be gone, on a hyperbolic trajectory, never to return. The probability is extraordinarily low. This is estimated to happen to a given star system less than once in the galaxy's lifetime. But the detection problem is the point. There is no observational program anywhere that would see it coming. It emits nothing. It occults stars, but the occultation of a 30-kilometer object at interstellar distance is not detectable by any instrument that exists. The first sign would be an unexplained perturbation in the orbits of the outer planets, and by the time that perturbation was large enough to distinguish from measurement error, the object would already be inside the solar system. That is what earns this entry its position. The warning time is not short because the object is fast. It is short because there is no channel through which a warning could arrive. It is worth spending a moment inside the silence of one of these objects, because the absence is the whole point. Imagine standing on a platform somewhere past the orbit of Neptune, with the Sun reduced to a very bright star behind you, and a 10 solar mass black hole passing at a distance of a few billion kilometers. There is nothing to see. Not a dark disk against the stars, because at that range it subtends an angle far below anything an eye or a telescope could resolve. Not a lensing halo, because the deflection is confined to a region a few hundred kilometers across at the object's own distance. Not a glow, because there is nothing falling into it. The star field ahead of you is completely unchanged. The only thing happening is in the numbers. Over months, the platform's trajectory bends by an amount that instruments would register as an anomaly and that no human sense could detect. Every object in the outer solar system is being pulled, very slightly, toward a point in the sky where there is nothing at all. The mass is 10 times the Sun's. The signature is a small, persistent error in the orbit solutions. And then it is passed, and the errors settle into a new configuration, and there is still nothing to see. There is one more population worth mentioning, because it demonstrates that the galaxy really does throw things. Hypervelocity stars are ordinary stars, moving fast enough to escape the Milky Way entirely. The standard mechanism, proposed by Jack Hills in 1988, is that a binary star system wanders too close to the black hole at the galactic center. The tidal field breaks the pair apart, capturing one star into a tight orbit around the black hole and flinging the other outward at enormous speed. Dozens have now been catalogued. The most extreme is S5HVS1, reported in 2019, traveling at about 1,755 kilometers per second, fast enough to cross a light year in under 200 years, and traceable backward to an ejection from the galactic center roughly 5 million years ago. It is leaving, and nothing will stop it. The relevance here is simple. The mechanism that ejects those stars is the same class of gravitational encounter that ejects compact objects, and compact objects are far harder to see. For every hypervelocity star that has been catalogued because it is bright, there is no way to know how many dark objects have been launched on similar trajectories. The galaxy is not a static arrangement. It is a system that occasionally flings its contents out into intergalactic space, and it does so without any of the objects involved being visible before or after. It is also worth appreciating how recent all of this knowledge is. In 1967, The word black hole had barely entered use. Cygnus X1 became the first plausible candidate in 1971. The first direct image of a black hole's shadow, the Event Horizon Telescope's picture of M87's central object, was released in 2019, and the image of Sagittarius A star followed in 2022. The first isolated stellar mass black hole was confirmed the same year. The first off-nuclear tidal disruption event was reported in 2025. An entire population of objects, numbering in the hundreds of millions, filling the galaxy we live in, and essentially all of the confirmed knowledge about the isolated ones, has been acquired within the last few years. A black hole has to arrive to do any harm. There is a class of event that does its harm from a distance, without ever coming any closer at all. Number 3. The kill radius. A supernova is the brightest thing an ordinary galaxy produces. A core collapse supernova, the death of a star more than about 8 times the Sun's mass, releases on the order of 10 to the 44th power joules as visible light over a period of weeks, briefly outshining every other star in its galaxy combined. It releases about 100 times more energy than that as neutrinos, in a burst lasting about 10 seconds, most of which passes through everything without interacting at all. The question that matters for this list is not how bright. It is how close is too close. Neil Gehrels and colleagues addressed it directly in a 2003 paper in the Astrophysical Journal, modeling the atmospheric chemistry consequences of a nearby supernova in detail. The mechanism is not what most people expect. It is not heat, and it is not blast. A supernova at any distance where it could plausibly occur delivers a negligible amount of heat to a planet, and there is no blast wave in any meaningful sense. The ejecta take thousands of years to travel light years and arrive as a thin plasma. What does the damage is chemistry. High-energy photons, X-rays and gamma rays, arriving at the speed of light, and later cosmic rays, arriving over the following centuries, penetrate the upper atmosphere and break molecular nitrogen apart. The freed nitrogen atoms combine with oxygen to form nitric oxide. Nitric oxide is a catalyst for ozone destruction. It reacts with ozone, produces nitrogen dioxide and molecular oxygen, and is then regenerated, so a single nitric oxide molecule can destroy thousands of ozone molecules before it is finally removed from the stratosphere. The process is the same chemistry and outline that operates in the well-studied ozone depletion cycles, driven far harder. Strip the ozone and the ultraviolet B flux at the surface rises sharply. Ultraviolet B is the band that damages DNA directly, and it is absorbed almost entirely by ozone and by nothing else in the atmosphere. It penetrates the upper few meters of clear ocean water, which is exactly where phytoplankton live, the organisms responsible for a large fraction of the planet's photosynthesis, and sitting at the base of the entire marine food web. Gehrels's calculation put the distance at which a typical core collapse supernova causes significant global ozone depletion at about 8 parsecs, 26 light-years. Later work has moved the number in both directions, depending on assumptions about how cosmic rays propagate through the interstellar magnetic field, how much of the supernova's high-energy output escapes, and how the atmosphere's circulation redistributes the damage. Figures in the range of 25 to 30 light-years are the ones usually quoted, and some analyses argue for a larger radius when the long cosmic ray tail is fully accounted for. Inside that radius, a supernova is not a spectacle. It is a multi-year ultraviolet event, followed by a longer cosmic ray exposure, followed by an ozone layer that takes years to decades to recover. And this is the point to return to something introduced much earlier on this list. The ozone layer is thin. Not thin in the way that clouds are thin in a way that is difficult to accept when you first hear the number. Ozone is a trace gas, even in the ozone layer itself. At altitudes between about 15 and 35 kilometers, it makes up only a few parts per million of the air. If all the ozone in Earth's entire atmosphere were brought down to sea level pressure and temperature and spread evenly around the planet, it would form a shell about 3 millimeters thick. 3 millimeters. Every complex organism that has ever lived on the surface of the land has lived underneath 3 millimeters of gas. Earlier on this list, that layer was being removed slowly by our own star over 1 billion years through a chain of chemistry that nothing can interrupt. Here it is being removed in weeks by a star that does not know Earth exists, that may not even be visible from here, and whose death was decided by its own mass 4 million years before anything on this planet had a spine. There are 2 candidate events in the geological record, and they are worth taking in order, because the second one comes with a test that could still be performed. The first is the late Ordovician extinction, about 445 million years ago. It is the second most severe of the 5 major extinctions, removing roughly 85% of species. Life at the time was almost entirely marine. The land was bare rock and at most a thin crust of primitive plants. The oceans held trilobites, brachiopods, graptolites, early corals, and the first jawed fish. The conventional explanation involves glaciation and sea level change. A large ice sheet formed on Gondwana, sea levels dropped, shallow marine habitats disappeared, and ocean chemistry shifted. That explanation accounts for a good deal of the pattern and is not disputed as a contributing factor. Adrian Malott and colleagues proposed an additional trigger in 2004 in the International Journal of Astrobiology, in a paper whose title was a question: did a gamma-ray burst initiate the late Ordovician mass extinction? Their argument was that a burst within about 6,000 light-years lasting 10 seconds would deplete global ozone by something on the order of 35% for a period of years, and that the resulting ultraviolet flux at the surface would produce a specific, checkable pattern of casualties. That is the strength of the proposal. It is not merely a plausible mechanism, it makes a prediction that can be tested against fossils. Because ultraviolet B penetrates only the upper layers of water, organisms living near the surface should die preferentially, while species living in deeper water should survive at higher rates. Ordinary glaciation-driven extinction predicts something close to the opposite pattern, because falling sea level destroys shallow shelf habitat. The Ordovician record shows the selectivity that the radiation hypothesis predicts. Surface-dwelling and shallow water taxa were disproportionately affected. Plankton in the upper water column suffered severely. That does not prove a gamma-ray burst occurred, because other mechanisms can produce some of the same signature, and the case remains a hypothesis rather than a conclusion. But the prediction was made in advance, and the pattern was there. The second candidate is the late Devonian, around 359 million years ago, at what is called the Hangenberg event, the final pulse of a prolonged extinction interval that reshaped marine ecosystems and hit the early forests hard. Brian Fields and colleagues published a proposal in the Proceedings of the National Academy of Sciences in 2020. Their starting evidence was unusual. The boundary rocks contain plant spores that are malformed and, in many cases, darkly pigmented, in a pattern consistent with ultraviolet damage sustained over an extended period, hundreds of thousands of years, not weeks. That duration is too long for a single gamma-ray burst, which does its damage in seconds and leaves an ozone layer that recovers within decades. Their proposal was one or more supernovae at roughly 65 light-years, spread over a period long enough to keep the ozone layer suppressed. A cluster of massive stars formed together will die within a few million years of each other, and if such a cluster passed near the solar system, the exposure would be repeated rather than singular. And they proposed a test. A supernova at that distance would deposit radioactive isotopes in the sediments, specifically plutonium-244 and samarium-146, both of which have half-lives long enough to survive from the Devonian in measurable quantities, and neither of which has any terrestrial source whatsoever. Finding either in rock of that age would settle the matter almost immediately. Nobody has looked hard enough yet. The measurement requires accelerator mass spectrometry on carefully selected samples, and it is difficult and expensive, and it has not been prioritized. A 359-million-year-old question with a clean experimental test attached is sitting there, unperformed. Then there is the nearest bright candidate, and it is the most famous star in this conversation. Betelgeuse, Alpha Orionis, the red shoulder of Orion, is a red supergiant of roughly 16 to 19 solar masses. It is one of the largest stars visible to the naked eye. Placed at the center of the solar system, its surface would extend somewhere between the orbits of Mars and Jupiter, depending on which measurement of its radius you accept and on what part of its pulsation cycle you catch it in. Its distance has been genuinely difficult to pin down. The star is so large and its surface so irregular that its apparent position shifts as convection cells the size of the inner solar system rise and fall on it, which corrupts parallax measurements. Estimates over the decades have ranged from 400 to 700 light-years. The most careful recent work, by Meredith Joyce and colleagues in 2020, combined asteroseismology, the analysis of the star's pulsation modes, with evolutionary modeling, and arrived at about 548 light-years, along with the conclusion that the star is currently burning helium in its core. That places the supernova roughly 100,000 years away, which is soon by stellar standards, and not soon by any other. At 548 light-years, Betelgeuse is nowhere near the kill radius, more than 20 times too far to cause meaningful ozone depletion. When it goes, it will be a spectacle, and nothing more. It will reach an apparent brightness comparable to a substantial fraction of the full moon, be plainly visible in daylight for weeks, remain a nighttime object bright enough to cast shadows and to read by for months, and then fade over a year or two, leaving Orion permanently missing a shoulder. Betelgeuse also demonstrates how much remains unknown about even the most closely studied stars in the sky. Between October 2019 and February 2020, it dimmed by more than a full magnitude, the most dramatic fading ever recorded for it. Speculation ran well ahead of the evidence, and for several months, a substantial part of the internet expected an imminent supernova. Miguel Montague and colleagues settled it in Nature in 2021, using direct imaging from the Very Large Telescope in Chile that actually resolved the star's disk. The star had ejected a substantial mass of material from its southern hemisphere. The material moved outward, cooled, and condensed into dust, which obscured part of the surface from our viewing angle. It was a dust cloud, not a death. And there is a newer development. Betelgeuse has a brightness variation with a period of about 6 years that no model of a single star could explain. A companion had been suspected for years and never seen, partly because finding a faint object next to one of the brightest stars in the sky is close to the hardest imaging problem there is. In 2025, using speckle imaging on the Gemini North Telescope, a faint stellar companion was directly detected, orbiting close enough to be inside Betelgeuse's own extended atmosphere. A companion star, hidden in plain sight, beside the most watched red supergiant in the northern sky, found in 2025. That is the honest state of the field in one example. The distance to the star was uncertain by 50% until 5 years ago, The most dramatic event in its recorded history was misread by a large fraction of the public and took 2 years to explain. And a second star was sitting next to it the entire time. So what is actually within range? Nothing at present, and that is a reassuring statement that comes with a specific time frame attached. There is no star within 30 light-years of the Sun that is a plausible supernova progenitor. The nearest candidate of any kind is IK Pegasi, about 154 light-years away, a binary system containing a white dwarf accreting from a companion, which makes it a candidate for a Type Ia supernova. Type Ia events have, if anything, a larger effective kill radius than core collapse events at the same distance, because a greater share of the energy emerges as high-energy photons early on. But IK Pegasi will not detonate for millions of years, and by then, its own motion through the galaxy will have carried it substantially farther away. Spica at about 250 light-years and Antares at about 550 are massive enough and are eventually going to explode, and both are far outside the range where it matters. There is also a useful empirical bound sitting in the material already covered. The local bubble, the cavity in the interstellar medium that this solar system currently occupies, was carved out by roughly 15 supernovae over the last 14 million years. Some of those were close. The iron 60 pulses in the ocean crusts, at around 2.5 and 6.5 million years ago, are the direct chemical evidence of at least 2 of them arriving here. Nothing died. There is no mass extinction in the record corresponding to either iron 60 pulse. The events were close enough to deliver measurable quantities of freshly forged radioactive material to Earth's surface, and not close enough to sterilize anything. Modeling of the progenitors places those explosions at roughly 90 to 100 parsecs, which is about 300 light-years, outside the kill radius, inside the delivery radius. That is an important calibration. It means the 26 light-year figure is not merely a model output. The geological record contains near misses that behaved as the models predict a near miss should behave. For scale on how often this happens at all, the Milky Way produces something like 1 to 3 supernovae per century. Almost all of them are hidden behind the dust of the galactic plane and are never seen from Earth. The last one visible to the naked eye was Kepler's star in 1604, observed by Johannes Kepler over the course of a year, appearing brighter than every planet. Before that, Tycho's star in 1572. Both were in the range of thousands of light-years, and both were purely spectacular. There has not been a naked-eye galactic supernova in 420 years, which is either a run of ordinary luck or a reminder of how much dust sits between here and most of the galaxy. One detail about the aftermath deserves mention, because it is the one thing about a near-miss supernova that would be visible from the ground. The nitric oxide produced in the upper atmosphere is not colorless. In sufficient quantity, nitrogen dioxide gives the sky a brownish cast, and models of a nearby supernova's atmospheric effects produce a persistent discoloration lasting years, a sky that is subtly the wrong color worldwide for longer than a childhood. Combined with an ozone layer at a fraction of its normal density and an ultraviolet flux high enough to damage exposed tissue within hours, the surface of the planet becomes hostile in a way that has no analog in ordinary experience. A bright day, a strange sky, and sunlight that is actively dangerous. There is a related object worth including here, because it produced the closest thing to a measured demonstration that anyone has. On the 27th of December, 2004, a giant flare erupted from a magnetar catalogued as SGR 1806-20. A magnetar is a neutron star with a magnetic field of extraordinary strength, 1,000 times stronger than an ordinary neutron star's and something like a quadrillion times Earth's. Occasionally, the crust of such a star fractures under magnetic stress and releases an enormous quantity of energy in a fraction of a second. This particular flare released more energy in 0.2 of a second than the Sun emits in 250,000 years. It arrived from a distance of roughly 50,000 light-years, from most of the way across the galaxy, with the entire galactic center region between us and it still ionized Earth's upper atmosphere measurably, disturbing the ionosphere in the same way a large solar flare does, and saturating the detectors on several spacecraft that happened to be pointed elsewhere. 50,000 light-years. That is the scale at which one of these objects can reach across a galaxy and physically alter the top of this planet's atmosphere. That measurement is the single most useful anchor in this entire entry, because everything else here is a model. Ozone depletion percentages are calculated. Kill radii are computed. The Ordovician and Devonian cases are inferences from patterns in rock. The December 2004 flare is a thing that actually happened, that was recorded by more than a dozen instruments, and that demonstrated a real physical effect on Earth from an object halfway across the galaxy. It also raises the obvious question of what such an event would do from closer. Estimates suggest that the same flare at 10 light-years would have destroyed a large fraction of the ozone layer. There is no magnetar within 10 light-years, and no reason to think one will be, since magnetars are young objects associated with recent massive star formation, and there is no such formation nearby. But the calibration is real. The last point on this entry is about recovery, and it is the reason a supernova is an extinction event rather than a sterilization event. The ozone layer is continuously regenerated. Ultraviolet light splits molecular oxygen, and the freed atoms combine with intact oxygen molecules to form ozone. The layer is not a static shell, but a steady state between production and destruction. Once the nitric oxide is flushed out of the stratosphere, which happens over years to a few decades, as air circulates down into the troposphere and the compounds are rained out, the ozone rebuilds. Years to decades is nothing in geological terms. It is a very long time biologically. A species that reproduces slowly, that lives at the surface, and that depends on a food web anchored in surface plankton, can be removed in that window and never come back, while the planet itself recovers completely and shows no sign a few thousand years later, except in the fossils. That asymmetry, a planet that heals in decades and a biosphere that does not, is what makes this class of event so difficult to detect in the record, and why the debate over the Ordovician has run for 20 years without resolution. The difference between a spectacle and an extinction is distance. Nothing else. The same event at 500 light-years is the most beautiful thing anyone alive has ever seen, and at 25 light-years, it is the end of most of what lives in the upper ocean. The star behaves identically in both cases. It has no idea either way. Everything on this list so far has come from somewhere else, from other stars, other galaxies, the deep future, the interstellar medium. The next entry comes from the one star we watch every single day. Number 2, the superflare clock. On the 1st of September 1859, an English amateur astronomer named Richard Carrington was doing what he did most clear mornings. He had built a private observatory at Redhill in Surrey, and his routine was to project the sun's image onto a screen and sketch the sunspots, day after day, building a record of their positions and motions. At about 11:18 in the morning, 2 patches of intensely bright white light appeared inside a large sunspot group. They were brighter than the surrounding photosphere by a wide margin, bright enough that Carrington initially suspected a fault in his equipment or a break in the cloud cover. He ran to find someone to witness it. By the time he returned, less than a minute later, the patches had already begun to fade. The whole event lasted about 5 minutes. Richard Hodgson, observing independently at Highgate, saw the same thing at the same time, which is the only reason the observation was accepted. Carrington's sketch and the 2 independent accounts constitute the first observation of a solar flare in human history. 17.5 hours later, the coronal mass ejection arrived. A coronal mass ejection is a different thing from a flare, though the two often occur together. A flare is a burst of radiation, arriving at the speed of light. A coronal mass ejection is a physical expulsion of billions of tons of magnetized plasma from the sun's corona, traveling outward at anywhere from 300 to 3,000 kilometers per second. When it strikes Earth's magnetosphere, it compresses and distorts the magnetic field, and the changing magnetic field induces electrical currents in anything conductive on the ground. The aurora that night was reported from Cuba, Hawaii, Colombia, and Queensland, latitudes where such things simply do not occur. Newspapers in Boston reported that people could read ordinary print by aurora light at 1 in the morning. Miners in the Rocky Mountains reportedly got up and made breakfast, assuming it was dawn. And the telegraph networks, which were the only significant electrical infrastructure the world possessed, failed across Europe and North America. Operators reported sparks jumping from equipment and, in some documented cases, paper catching fire. On several lines, the induced current was strong enough that operators disconnected their batteries entirely and continued sending messages using the current the atmosphere was supplying. Reconstructions of the storm's intensity from magnetometer records of the period put the disturbance storm time index somewhere between -850 and -1760 nanotesla, depending on the analysis. Either figure makes it the most intense geomagnetic storm in the instrumental record. The world of 1859 had almost nothing electrical to break. That is the entire problem with this entry, stated in one sentence. The largest storm on record struck a civilization whose total exposure was a few 100,000 kilometers of telegraph wire, and it burned out relays and set fire to paper. There was no grid, no electronics, no satellites, no pumps, no refrigeration, no digital records, and nothing that stopped working when the wires misbehaved. Stand in a telegraph office on the morning of the 2nd of September, 1859. The operator has disconnected the batteries. He did this 20 minutes ago because the line was behaving strangely, the sounder clicking at intervals that corresponded to nothing anyone was sending, the key growing warm under his hand. Disconnecting the batteries should silence a telegraph line completely. It is the simplest possible diagnostic. The instrument is still working. There is current in the wire, and it is not coming from this building. It is coming from a copper line strung on poles across 150 miles of countryside, and something is driving a voltage along its length from end to end. 2 operators, one in Boston and one in Portland, will spend the better part of 2 hours that night sending messages to each other on a dead circuit, with no power source connected at either end, and will note it in their logs as a curiosity. Outside the window, the sky is red. Not at the horizon, overhead, across the whole visible dome, shifting slowly in curtains and folds, at a latitude that has no business seeing aurora at all. People have come out into the street. Some of them think the city is on fire somewhere out of sight. Some of them think it is the end of the world, and say so, and are not entirely alone in the opinion. Nothing in the room can be damaged by any of this beyond a scorched relay and a sheet of paper. The most complex electrical device within 100 miles is the instrument on the desk, and it is a magnet, a spring, and a piece of iron. In the morning, the operator will reconnect the batteries, and the line will work normally, and the entire episode will be a story he tells for the rest of his life. The modern demonstration of what the same physics does to a modern system arrived on the 13th of March 1989. A geomagnetic storm, far smaller than the 1859 event, induced currents in the long high-voltage transmission lines of the Hydro-Quebec grid. Quebec is a particularly exposed case. The grid runs long distances across ancient igneous rock of very low conductivity, which forces the induced currents into the transmission lines rather than allowing them to dissipate into the ground. The induced direct current flowed through transformers designed for alternating current and drove their magnetic cores into saturation, which generates harmonics, which triggered protective relays. 7 static compensators on the Legrand network tripped in sequence. The entire provincial grid collapsed in 92 seconds. 6 million people lost power for roughly 9 hours in Canada in March. The same storm damaged a large transformer at the Salem nuclear plant in New Jersey, a component that took months to replace, and pushed auroras as far south as Texas and Cuba. 92 seconds is the number that ought to stay with people. Not because the outcome was catastrophic, it was serious, and it was survived. But because the collapse of a major grid, once it begins, is a cascade governed by relay logic, operating in milliseconds, and there is no human decision anywhere in the sequence. And on the 23rd of July 2012, the Sun launched a coronal mass ejection of Carrington class or greater directly across Earth's orbital path. Earth had passed through that point in its orbit 9 days earlier. The event was measured in full by the Stereo A spacecraft, which happened to be in the right place, and Daniel Baker and colleagues published the analysis in 2013. The ejection was moving at over 2,000 kilometers per second and carried an unusually strong southward magnetic field, which is the configuration that couples most efficiently with Earth's magnetosphere. Their assessment was that it would have produced a geomagnetic storm comparable to or exceeding 1859. Pete Riley, working from the statistical distribution of extreme space weather events, published an estimate in 2012 of roughly a 12% probability per decade for a Carrington-class storm to strike Earth. That number has been debated and revised in both directions since, but it has not been revised to anything reassuring. Then the record got much older and much worse. In 2012, Fusa Miyake and colleagues at Nagoya University published a paper in Nature that changed the field. They had been measuring carbon-14 in the annual growth rings of Japanese cedar trees, working ring by ring across a long span of history. Carbon-14 is produced in the upper atmosphere when cosmic ray secondaries, neutrons mostly, strike nitrogen. The production rate therefore tracks the flux of energetic particles arriving at the top of the atmosphere. The carbon is incorporated into carbon dioxide, taken up by plants, and locked into that year's growth ring. A tree ring is an annual sample of the atmosphere's radiocarbon content, and it is dated to the exact year by counting. In the rings corresponding to the years 774 and 775 of the Common Era, they found a spike. Carbon-14 jumped by about 1.2% in a single year. That is enormous. Ordinary solar cycle variation moves the radiocarbon level by a small fraction of a percent over 11 years. A 1.2% jump in 12 months required a particle event roughly 10 to 20 times larger than the Carrington event in terms of energetic particle output. The finding was checked immediately and independently in tree rings from Germany, from the United States, from New Zealand, different hemispheres, different species, different laboratories. The spike was in all of them at exactly the same year. It was also found in beryllium-10 in Greenland and Antarctic ice cores, which rules out any biological or regional explanation, since beryllium-10 follows a completely different pathway from atmosphere to archive. A second spike was found at 993 to 994. Then a third, older one, at 663, before the Common Era. Then more, 52, 59, and 71, 76, before the Common Era, the latter being for some years the largest known. And in 2025, analysis of an event around 12,350 before the Common Era identified the strongest solar particle event yet found in any record, roughly 18% larger than the 775 event. These are now called Miyake events. At least 6 are confirmed in about 14,000 years of record, and the search continues in older material. There is a wonderful use these events have been put to, which has nothing to do with danger and everything to do with what a precisely dated global marker is worth. The Norse settlement at Lanceau Meadows in Newfoundland has been known since 1960 and has always been dated only approximately to somewhere in the 11th century. Margot Quaitims and colleagues, publishing in Nature in 2022, took wooden objects from the site, pieces with cut marks made by metal tools, which the indigenous peoples of the region did not use, and located the 993 carbon-14 spike in the growth rings. Then they simply counted rings outward from the marker to the bark edge. The trees were felled in the year 1021. Not approximately. Exactly. A solar storm in the year 993, recorded simultaneously in every tree on Earth, is the reason we know the precise year Europeans were cutting timber in North America. That is the same phenomenon that this entry is about, viewed from the other side. And now the clock, which is where this entry earns its position. Much earlier on this list, at number 6, there was a rhythm in the fossil record with no mechanism attached, a clock nobody set, ticking on an interval of roughly 27 million years, so long that the entire history of primates fits comfortably inside a fraction of one cycle. That interval is so far outside human experience that it functions more as a curiosity than a concern. The phrase belongs here too, and the interval has collapsed. Hiroyuki Miyahara and colleagues published a paper in Nature in 2012, the same year as Miyake's, examining the Kepler Space Telescope's photometry of solar-type stars. Kepler was designed to find planets by watching for the tiny dimming of a transit, which means it produced extremely precise brightness measurements for enormous numbers of stars over years. That same data records flares as brief upward spikes. Miyahara's team found superflares, events releasing 10 to the 33rd power ergs or more, up to 10 to the 36th, 1,000 times the energy of the largest solar flare ever directly observed. They found them on ordinary sun-like stars. On the fastest rotating and most magnetically active stars, they were common. On slowly rotating stars resembling the Sun, the estimated rate was something like 1 every 800 to 5,000 years, which was startling but manageable. Then, in December of 2024, Valery Vassiliev and colleagues published a considerably more careful analysis in Science. They took Kepler's full catalogue and applied strict selection criteria to isolate stars genuinely comparable to the Sun in temperature, radius, and rotation rate, and, critically, they removed contamination from neighboring stars blended into the same pixels, which had inflated earlier flare counts. Their sample was 56,450 Sun-like stars, and within it they identified 2,889 superflares on 2,527 of those stars. The rate they derived for superflares of 10 to the 34th power ergs and above was approximately 1 per star per century. Not once per few thousand years. Once per century. That is the shifted meaning of the phrase. At number 6, the clock's tick was longer than the existence of our genus, which made it an abstraction. Here, the tick is shorter than a human life. If the result holds, and it is one result, from one instrument, using one selection method, and it will be tested against data from the TESS mission and from ground-based surveys for years, then the Sun is capable of producing an event 100 times larger than anything in the instrumental record, on an interval that a person could plausibly live through. The Miyake events are the corroboration from the other direction. 6 confirmed particle events in 14,000 years is not once per century, but the tree ring and ice core records only register the very largest events, and only those with a strong particle component. The statistical shape of the two datasets is compatible. The consequence for a modern civilization is not biological. Nobody is harmed directly by a geomagnetic storm at ground level. The atmosphere and the magnetosphere handle the radiation for anyone who is not in orbit or at high altitude. The consequence is infrastructural, and it concentrates in one component. Geomagnetically induced currents flow through long conductors, high-voltage transmission lines, pipelines, railway signaling, undersea communications cables. When that current reaches a large power transformer, it drives the magnetic core into saturation. A saturated transformer draws enormous reactive power, generates harmonics that confuse protective equipment, and heats internally in ways it was never designed to tolerate. In the worst case, the winding insulation fails and the transformer is destroyed. Extra high-voltage transformers are not commodity items. They are custom-engineered for a specific installation, weigh hundreds of tons, are manufactured by a small number of firms worldwide, take a year or more to build, and are not stockpiled in significant numbers. Losing a handful is manageable. Losing dozens simultaneously across a continent is a different kind of problem. Lloyd's of London published an assessment in 2013 estimating that an extreme geomagnetic storm affecting North America could produce between $600 billion and $2.6 trillion in damage, with restoration times in the worst affected regions measured in months to years. Which brings this entry to the number that determines its place on this list. Space weather forecasting relies on spacecraft stationed at the first Lagrange point, a gravitational balance point about 1.5 million kilometers sunward of Earth, where a satellite can hover permanently between us and the Sun. The ACE spacecraft has been there since 1997. Discover joined it in 2015. Both carry instruments that sample the solar wind directly, its speed, density, and most importantly, the orientation of its embedded magnetic field. That last quantity is the one that cannot be measured any other way. A coronal mass ejection with a northward-pointing magnetic field couples poorly with Earth's magnetosphere and produces a modest storm. The identical ejection with a southward-pointing field couples efficiently and produces a severe one. There is no way to determine the orientation from a distance. It has to be measured in place as the cloud passes the spacecraft. A coronal mass ejection traveling at 2,000 kilometers per second covers the distance from the first Lagrange point to Earth in about 12.5 minutes. That is the warning. Roughly 15 minutes between confident knowledge that a severe storm is arriving and its arrival. Enough time, if the right procedures are in place and the right people are watching, to reduce loading on vulnerable transformers, to shut down some equipment, and to alert operators. Not enough time for anything that requires a decision to be discussed. There is a longer lead available and it is far less certain. The flare itself is visible immediately. The light takes 8 minutes and 20 seconds to arrive, and solar observatories see it as it happens. From the flare's characteristics and coronagraph imagery of the ejection leaving the Sun, forecasters can estimate an arrival time somewhere between 15 and 72 hours later, with an uncertainty commonly measured in many hours. What they cannot forecast at that range is the magnetic orientation, which is the difference between an inconvenience and a catastrophe. And the flare's own radiation, the X-rays and extreme ultraviolet, arrives with no warning at all, because it travels at the speed of light, alongside the light that reveals it. That radiation ionizes the upper atmosphere within seconds and produces immediate high-frequency radio blackouts on the sunlit side of the planet. The largest directly observed flare of the modern era, on the 4th of November 2003, saturated the X-ray sensors on the GOES satellites and was later reconstructed at roughly X45, several times larger than anything the instruments were built to measure. So the ladder this list has been descending arrives here at 15 minutes. We began with warning times that were not measurable because the events lie beyond the existence of matter. We passed 100 billion years, then a billion, then hundreds of millions, then tens of millions, then the few thousand years between a nearby star's death and the arrival of its cosmic rays. Now we are at a quarter of an hour, on an event whose recurrence interval may be a single human lifetime, affecting infrastructure that every person in a developed country depends on for water, food storage, payment, communication, and medicine. 15 minutes is not much warning. There is exactly one entry left on this list, and it does not offer any. Number 1. The burst that arrives with its own warning. The discovery was an accident of the Cold War. In the 1960s, the United States launched a series of satellites called Vela, in pairs, into very high orbits. Their purpose was compliance verification. The Partial Test Ban Treaty of 1963 prohibited nuclear testing in the atmosphere, underwater and in space, and the Vela satellites carried gamma-ray, X-ray, and neutron detectors designed to catch anyone conducting a clandestine test beyond the atmosphere, including, in principle, a test conducted on the far side of the Moon. On the 2nd of July 1967, Vela 4 recorded a flash of gamma radiation. It did not look like a bomb. A nuclear detonation produces a characteristic intensity profile, a sharp initial spike, a dip, then a second, broader peak. This signal had a different shape entirely, an irregular rise and a slow decay, with structure that no weapon produces. Ray Klebezadel, Ian Strong, and Roy Olson at Los Alamos began collecting these events. Over the following 6 years, they accumulated 16 of them, and by comparing arrival times across the widely separated satellites, they were able to triangulate rough directions. The sources were not on Earth. They were not on the Moon. They were not in the solar system. The results were classified for 6 years. The paper finally appeared in 1973 under the deliberately unexciting title Observations of Gamma-ray Bursts of Cosmic Origin. 16 bursts, no explanation, no distance, no mechanism. For the next 2 decades, the central question was whether the bursts came from our own galaxy or from the universe at large, and the difference mattered enormously because the required energy scales with the square of the distance. If they were nearby neutron stars in the Milky Way's disk, they were modest events. If they were cosmological, they were the most energetic explosions since the Big Bang, by orders of magnitude. The answer came from the Burst and Transient Source Experiment, BATSE, aboard the Compton Gamma Ray Observatory, which operated from 1991 to 2000. BATSE recorded 2,704 bursts over 9 years, and the crucial result was not about any individual burst. It was about the map. If the sources were in the disk of our galaxy, they would concentrate toward the galactic plane, because that is where the disk is. If they were in a halo around our galaxy, they would concentrate toward the galactic center. The BATSE distribution did neither. It was isotropic, the same in every direction, to a high degree of precision, and it showed a deficit of faint bursts relative to what an infinite uniform distribution would produce, which is the signature of seeing out to a distance where the universe's structure and expansion begin to matter. They were extragalactic, which meant the energies were enormous. A long gamma-ray burst, if you assume it radiates equally in all directions, implies a release on the order of 10 to the 54th power ergs. That is more energy than the Sun will emit across its entire 10 billion-year main sequence lifetime, delivered in a matter of seconds. It does not radiate equally in all directions, and that fact is the single most important thing about this entry. The emission is collimated into narrow jets, with opening angles typically between about 2 and 10 degrees. Beaming reduces the true energy requirement by a factor of 100 or more, which brings it into the range that a stellar collapse can actually supply. The evidence for beaming is direct. The afterglow light curves of many bursts show a characteristic steepening, a jet break, at the point where the jet has decelerated enough that its edges become visible, and the timing of that break gives the opening angle. Beaming is why gamma-ray bursts are survivable at all. Only a small fraction of the universe lies inside any given burst's cone. It is also why the ones that matter are the ones nobody would see coming, because to be harmed by one, you have to be inside the beam. The mechanisms are now reasonably well understood, and there are two of them. The duration distribution of gamma-ray bursts is bimodal. There is a population lasting less than about 2 seconds, and a population lasting longer, and the two have different spectra, different host environments, and different origins. Long bursts come from collapsars. Stan Woosley proposed the model in 1993. A massive star, rapidly rotating and low in heavy elements, reaches the end of its life, and its core collapses directly to a black hole. Because the star is rotating fast, the infalling material cannot go straight in. It forms an accretion disk around the new black hole, and the disk drives a pair of relativistic jets along the rotation axis. The jets bore through the collapsing star, break out of its surface, and the gamma rays are produced when shells of material within the jet collide with each other at slightly different velocities. The observational confirmation came in 1998. A burst catalogued as GRB 1998BW was found to coincide, in position and time, with an unusual and very energetic supernova in a nearby galaxy. A supernova with no hydrogen lines and unusually broad features, indicating extremely fast ejecta. That was the first direct link between a gamma-ray burst and the death of a massive star, and many more have been established since. Short bursts come from mergers of compact objects, 2 neutron stars, or a neutron star and a black hole. That was the leading hypothesis for years, and it was confirmed spectacularly on the 17th of August, 2017. At 12 minutes past 1 in the afternoon, Universal Time, the LIGO detectors in Louisiana and Washington and the Virgo detector in Italy recorded a gravitational wave signal lasting about 100 seconds, with the characteristic rising chirp of 2 neutron stars spiraling together. 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope recorded a short gamma-ray burst. Within 11 hours, telescopes on the ground had identified the source in the galaxy NGC 4993, about 130 million light-years away, and over the following days, roughly 70 observatories across every wavelength watched the aftermath. The kilonova, the radioactive glow of freshly synthesized heavy elements, including a substantial fraction of the universe's gold and platinum. That event is the origin of the only warning time this entry contains. 1.7 seconds. The gravitational waves arrived first because they were emitted slightly earlier in the merger sequence, and because they travel through the star's debris without impediment, while the gamma rays have to wait for the jet to break out. 1.7 seconds is also, incidentally, one of the most precise confirmations ever made that gravitational waves travel at exactly the speed of light. Across 130 million light-years of travel, the two signals arrived within 2 seconds of each other. The brightest burst ever recorded arrived on the 9th of October, 2022, and it was so far beyond the others that it acquired a nickname within days. Astronomers called it the Boat, the brightest of all time. GRB 2022-1009A came from a galaxy at a redshift of about 0.151, roughly 2.4 billion light-years away. That is far. It is a substantial fraction of the way across the observable universe by the standards of ordinary astronomy, and it is very close by the standards of gamma-ray bursts, most of which come from much greater distances. It saturated everything. Instruments specifically built to measure gamma-ray bursts could not measure this one properly because it exceeded their dynamic range and drove their detectors into pile-up. Reconstructing its true brightness required careful modeling of how each instrument had failed. The Lhasa Observatory in China, which detects very high-energy gamma rays through the air showers they produce in the atmosphere, recorded photons from the burst at energies up to 18 tera-electron volts, by a wide margin the highest energy photons ever detected from a gamma-ray burst, and high enough that their survival across 2 billion light-years of intergalactic space is itself a mild puzzle. And Earth noticed. Instruments monitoring the ionosphere, the ionized upper layer of the atmosphere, between roughly 60 and 1,000 kilometers up, which reflects radio waves and whose conductivity is measured continuously by a network of ground stations and satellites, recorded a disturbance coincident with the burst's arrival. An explosion 2.4 billion light-years away physically altered the top of this planet's atmosphere. The ionization it produced was equivalent to a substantial solar flare from a source outside our galaxy, outside our galactic neighborhood, from a distance where the light that arrived had left before multicellular life existed on Earth. Estimates place an event of that brightness at roughly once in 10,000 years, which means the odds of it happening during the 60-year window in which humans have had instruments capable of measuring it are around 1 in 170. Now, the theory that closes this list. In 2014, Tzvi Piran and Raul Jimenez published a paper in Physical Review Letters titled On the Role of Gamma-Ray Bursts on Life Extinction in the Universe. Their method was to combine 3 things that were each reasonably well measured. First, the observed rate of long gamma-ray bursts per unit of star formation. Second, the strong dependence of that rate on metallicity. Long bursts occur overwhelmingly in galaxies poor in heavy elements, because massive stars in metal-rich environments lose too much mass to stellar winds to retain the rapid rotation a collapsar requires. Third, the threshold distance at which a burst causes severe ozone depletion, which they took from the same body of atmospheric modeling that produced the numbers at number 3, roughly 6,000 light-years for a burst aimed at you. Then they asked a straightforward question. Given all of that, how often is a given planet sterilized of complex life? The answers are the reason this entry sits at number 1. For a planet at Earth's distance from the galactic center, about 26,000 light-years out, in a relatively quiet region between spiral arms, the probability of experiencing a life-threatening gamma-ray burst in the last 500 million years is roughly 50%. 50%. Over the interval that contains essentially the entire history of complex animal life on this planet, the odds of a sterilizing event were approximately even, and we appear to have been on the fortunate side of the coin, with the possible exception of the Ordovician. Move inward, and it gets much worse. Within about 4 kiloparsecs of the galactic center, roughly 13,000 light-years, where stellar density is far higher, they put the probability of a lethal burst at about 95%. The inner region of this galaxy, an enormous volume containing an enormous number of stars, many of them older than the Sun and hosting planets billions of years more mature, is, on this analysis, effectively uninhabitable for anything that takes hundreds of millions of years to develop. And because long bursts favor low metallicity environments, the early universe was dramatically more hostile than the present one. Metallicity rises over cosmic time as generations of stars enrich their galaxies. Piran and Jimenez estimate that complex life was likely impossible almost everywhere until the universe was several billion years old, and that even today, life is plausible in only about 10% of galaxies, the rest being too small, too dense, or too metal-poor to permit it. Sit with what that implies about the first 9 billion years of this universe. Not empty, not lifeless in the microbial sense. Simple life is far more resistant to radiation than complex life, and there is no particular reason to think it would be prevented. But repeatedly, thoroughly, and across essentially every galaxy, any biosphere that had begun to develop anything requiring long, uninterrupted stretches of stability would have been reset, and then reset again and again in every direction for a span of time longer than the Earth has existed. On this account, we are not somewhere in the middle of a long cosmic story. We are near the beginning of the only part of it in which the story can be told, the late, enriched, quiet epoch, in the outer suburbs of a large galaxy, after most of the shooting has stopped. The argument is not settled. The rate calculations depend on the metallicity dependence, which is measured from a modest sample of bursts with identified hosts. The kill radius depends on atmospheric modeling with real uncertainties. Other groups have argued for a substantially smaller effect. But it is a serious paper by serious people, and it remains one of the few quantitative attempts to say where and when in the universe complex life is even possible. And then there is the specific object, which is the part of this entry that has kept people up at night for 25 years. In 1999, Peter Tuthill, John Monnier, and William Danchi published images in Nature of a system catalogued as WR-104, about 8,000 light-years away in Sagittarius. WR-104 is a Wolf-Rayet binary. A Wolf-Rayet star is a massive star in a late evolutionary stage that has shed its outer hydrogen envelope entirely, exposing its helium and heavier element interior, and is driving an extremely powerful stellar wind. In this system, a Wolf-Rayet star orbits a hot, massive companion every 241 days, and where the two winds collide, carbon-rich dust condenses. As the pair orbits, the dust-producing region rotates with them, and the outflowing dust traces a spiral, a pinwheel, expanding outward at about 1,000 kilometers per second. The images resolved that spiral directly using interferometry on the Keck telescope, and it was the first structure of its kind ever imaged. It is genuinely beautiful, and it was described at the time in exactly those terms. Then somebody thought about the geometry. A spiral is a flat structure. Viewed edge-on, it looks like a line. Viewed at an angle, it looks like an ellipse. The spiral in WR-104 appears almost perfectly circular, which means we are looking almost straight down the system's rotation axis. In 2008, Tuthill and colleagues published an analysis putting the inclination within about 16 degrees of pole-on. The rotation axis is where the jets come out. A Wolf-Rayet star of that mass is a strong candidate to end as a collapsar, and a collapsar produces its jets along its rotation axis, and a jet opening angle is a few degrees, and 16 degrees is uncomfortably close to a few. The honest status matters here more than anywhere else on this list, so it should be stated carefully. Later work has pushed back substantially. Spectroscopic studies of the system's emission lines, including work by Grant Hill and colleagues, derived orbital inclinations inconsistent with a pole-on view, closer to 30 or 40 degrees. Anthony Soulain and colleagues have argued from detailed dust modeling that the spiral's apparent circularity can be reproduced without the system being aimed at us, because the dust distribution is not a simple flat sheet, and the projection effects are more complicated than the original analysis assumed. The current consensus is that WR104 is probably not pointed at Earth. Probably. It is a system 8,000 light-years away whose inclination has been measured by several methods that do not agree, and the difference between the answers is the difference between a distant curiosity and a loaded object. And even in the worst case, 8,000 light-years is at the outer edge of the range where the effects would be severe rather than catastrophic. The modeling suggests significant ozone depletion, not sterilization. It is also worth noting that the Milky Way is a comparatively poor host for long gamma-ray bursts. Our galaxy is metal-rich, and metal-rich galaxies produce few collapsars. Estimates of the rate for a galaxy like ours run around one long burst per 100,000 to one per million years, and of those, only a small fraction would be beamed anywhere near Earth. The combined probability of a lethal burst reaching this planet in any given million-year interval is low. Low is not zero, and the geological record at number 3 contains at least one extinction whose pattern of casualties matches what the radiation hypothesis predicts. So here is what arrival would actually be. It is an ordinary evening. The sky is whatever the sky is where you are, clear or overcast, or half-lit by a city. Nothing is approaching. There is no object growing brighter over weeks, no comet, no new star, nothing in any catalogue that anyone would have flagged. 8,000 light-years away, or 6,000, or 4, a star that has been quietly running out of fuel for 4 million years reaches the end of it, and its core falls in, and a jet punches out along an axis that happens to pass through this part of the sky. The gamma rays travel for thousands of years across the interstellar medium, unimpeded, and arrive. And nothing visible happens. That is the part people get wrong. There is no flash. Gamma rays are absorbed high in the atmosphere, tens of kilometers up, and the energy is deposited there rather than at the surface. Depending on the burst's intensity and whether it is day or night where you stand, the sky might briefly show a faint glow at the top of the atmosphere, or it might show nothing at all. Instruments would register it in the same instant. A person standing outside would notice, at most, an odd shimmer. The damage begins in the chemistry, and it is silent. Nitric oxide is manufactured across the upper atmosphere in a few seconds. Over the following weeks, the circulation carries it into the stratosphere, and the ozone begins to go. Over the following months, the sky slowly acquires a faint brownish cast, and the ultraviolet at the surface climbs. Over the following years, the plankton in the upper ocean fail, and then everything that eats them. The event is over in 10 seconds. The consequences take a decade to arrive and 100,000 years to resolve. And the whole time, from the moment the star's core collapsed to the moment the first molecule of ozone was destroyed, there was no interval in which anyone could have known. That is the phrase this list has been carrying since number 11, and it returns here meaning the opposite of what it meant then. At number 11, the light and the news arrived together, described a limit on knowledge. Light is the only messenger cosmology has, and when the light stops arriving, the knowledge stops with it, and a future observer is left with a perfectly reasonable and completely wrong picture of the universe. Here, The same sentence describes the structure of the danger. Gamma rays travel at exactly the speed of light. There is no signal that outruns them. The gravitational waves from a merger by 1.7 seconds. A collapsar offers not even that, because the star gives no external sign in the hours before it fails. The event and the information about the event are the same thing, moving at the same speed, arriving in the same instant. Every other entry on this list, however grim, comes with time. 10 to the 100th power years for the heat death. 100 billion for the loss of the evidence. 1 billion for the end of the biosphere. 4 billion for the galaxies. Hundreds of millions for the planets. Tens of millions for whatever is keeping time in the fossil record. Thousands for a cloud of interstellar gas or a nearby supernova. 15 minutes for the sun. This one comes with none. That is the only reason it is number one. That is the whole list, and it is worth saying plainly what all 12 of these have in common before this ends. Every one of them is a description of time. That was the axis from the first sentence, and it has held all the way down how long the universe has, how long the evidence has, how long this planet has, how long a warning would be. Not one of these theories is about malice or design or anything aimed at anyone. The sun brightens because helium is heavier than hydrogen. Mercury's orbit stretches because two precession rates drift into step. A star 8,000 light-years away releases its jets along whatever axis it happens to be spinning around, and has no more knowledge of this planet than this planet has of it. And of the 12, 11 operate on timescales longer than any civilization has yet existed, and the 12th would take out transformers. There is a version of this list that is frightening, and it is the version where a person reads each entry as a thing that might happen tonight. There is another version, which is the accurate one, in which these are the honest boundaries of a long, quiet, still-running experiment, the outer edges of what is known about how much time there is, worked out by people counting tree rings, typing fossil ranges into databases, following one microlensing event for 11 years, and sitting under a mountain watching 50,000 tons of water for a proton that never decayed. None of it needs anything from you tonight. Sleep well, and good night.